Hello there, Chris, VK3AML from Melbourne, Australia, again starting the stream, hoping everybody's had a good week. This tradition, I suppose you'd call it in ham radio, was begun by my predecessor with my call sign, the late Tony Sanderson, VK3AML, with his crossbands, which began back about 1972, a full 50 years ago now. Were carried on as a Saturday night tradition by VK3ASE, Dave Stewart. And now that Dave has vacated the bands for while he pursues, I think, a shortwave broadcasting license for about 2.3 megahertz, we'll continue with the same theme that Dave and Tony have done before me, with a slightly enhanced video version of what they had done. That is these YouTube live streams every Saturday night at 9:30 p.m. The usual format is that I run some pre-recorded material related to various aspects of the hobby, technology, history, communications generally, and then after 90 minutes at about 11 p.m. we throw it open for a QSO on 2 meters FM, which anybody within range of us here, which is about 100 kilometres from Melbourne, is welcome to join in on. So that being said, and I see my stream is there, we'll go on the air. It's 9:30. Hello, this is VK3 Alpha Mike Lima. Checking our output, it looks like we've got the usual 40 watts. And streaming on YouTube live stream. If you care to Google VK3AML 18 June 2022, that is, Google the phrase VK3AML 18 June 2022, you should find this stream. If you have trouble finding it there, look up my YouTube channel, which is under the name, single word, Oz Radio Historian, AUSRADIOHISTORIAN, Oz Radio Historian, and the latest clip should be this live stream. Okay, that being said, we have a fairly full program tonight. We'll be talking about an up-and-coming method of communication on HF radio, and that is Orthogonal Frequency Division Multiplexing. Quite a mouthful, but it refers to that multi-subcarrier technique that's used for DRM, shortwave high-quality intercontinental broadcasting, as well as EasyPal digital slow scan, which I'll show you a little bit of now. This is OFDM multiple subcarriers as seen in the waterfall display of a web-based SDR receiver on the left, while on the right you'll see the decoding software called EasyPal, devised by an Australian, Erickson VK4 Alpha Echo Sierra. Now we're receiving multiple subcarriers, which you can see in the waterfall display, both on the web SDR and on EasyPal, on the left-hand side of the EasyPal frame. And you'll notice that with the multiple subcarriers, we can actually see the effects of selective fade on the signal as a series of oblique, generally, dark bands, indicating that on 80 metres, and I'm receiving this from a French source, the French EasyPal digital slow scan group, and here comes their next image. And the French have a habit of transmitting interesting stuff. As you'll see, the quality is way ahead of any analog slow scan, but this particular iteration of slow scan digital, it cheats a little bit. They're transmitting on that multi-subcarrier the URL of a cache which the distant computer is commanded to look at. This is just a secure way of transmitting a URL, but you can transmit a whole image through this multi-subcarrier technique. This is one of the most common amateur usages for it. You see the oblique lines on the stream that indicates the selective fade of characteristic of multipath on ham radio. In that particular case, the separation of the selective fades are about a kilohertz apart and moving through the passband. Oh, those French. They do go for good-looking women. A tradition that was established, I think, by Maurice Chevalier and has been carried on ever since. Mind you, some of the women that they transmit aren't so attractive, like this little Zumba fellow. But this method of transmitting multiple subcarriers is a great way of transmitting digital information. And the way it does it is quite complex. Jeremy Clark VE3PKC of Toronto is a senior telecommunications engineer and the author of several ebooks on telecommunications, navigation and electronics. And in a couple of minutes he'll be explaining the finer points of OFDM and its application to ham radio on HF. This is just one of those applications. High quality transmissions of audio are another. And here comes another picture. Yes, the French have a thing for attractive women. Well, doesn't everybody? And that gives you an idea of one potential application of orthogonal frequency division multiplex. Of course, it's much more generally used than that, including on 5G and, as I said before, international shortwave broadcasting. So here's Jeremy, VE3PKC of Toronto, to tell you a bit more about this intriguing medium. Please note that this lecture assumes a basic knowledge of mathematics and communications engineering, so if that's a little bit challenging to you, it might be worthwhile jumping forward another 30 minutes or coming back at about 10 o'clock when we have another lecture by Phil Erickson W1PJE on ionospheric propagation and prediction, which is a slightly more friendly topic. For the moment, here's Jeremy to tell us something about the requirements and the advantages of OFDM, Orthogonal Frequency Division Multiplex.
Good morning, it's Jeremy. It's Thursday, May the 14th, lockdown Thursday, and it's freezing outside. It's like winter. Today I want to talk about OFDM, which stands for Orthogonal Frequency Division Multiplexing. It's a telecommunications technology which is used pretty well everywhere now. Typical applications might be in digital shortwave broadcasting, DRM. It's used on cable television systems, discrete multitone. It's used in 4G. It's used in LTE. It's used in 5G. It's used pretty well everywhere. And the idea behind OFDM, let's say you have a given restricted channel bandwidth and you want to cram as many bits per through that bandwidth. What you can do, for instance, is you can have, let's say, a Qam signal or a QPS signal taking up the whole channel, and you put all basically your bits in one basket. Now what happens in that channel, let's say, for instance, if you get some form of multipath, you can have a selective fade within the channel, so a portion of that spectrum gets screwed up. Now if you just have one carrier taking up the whole bandwidth, then you'll lose everything. In OFDM, what you do is you split your data up into many, many parallel channels. So let's say a selective fade goes through, it knocks out part of the channel. Your data can be split in such a way or coded in such a way that only that portion is lost and the rest of it gets through. So that's kind of the idea behind OFDM. If we look at, let's say, the history of OFDM, In a sense, it's nothing new. If you go back to the, let's say the 1800s, when we started with electronic communication with telegraphs, when Morse used his Morse code and telegraph systems expanded all over the planet. Essentially, when you think about it, that was the first internet. Generally, the telegraph system needed space to run the wires. So a telegraph system consisted of basically a battery, a couple of wires, and a key. A key would put current on the line at the transmitter, and at the receive end, what you would have is you would have a magnet with some form of a sounder. So when the key closed, current would flow down the wire to the sounder. The magnet will pull the sounder down. It would make a clicking noise. So that's basically the telegraph. Now you could have two wires, or you could basically have a one wire and a ground return. In the 80s, I worked on a telecom system in Southeast Asia, and there was a telegraph system parallel to the railway where we were working. And that system was put in by the Dutch in the 1800s, and 100 years later, the system was still working well. It was one single galvanized steel or iron galvanized wire, and the return path was actually the ground, which is fairly wet. It was a tropical country, and they had Leyden jars for batteries, and the system worked really well. So here is actually this is my Morse code key that I used in 1966 to get my ham license. I learned how to tap Morse code here. So I've got a little telegraph system set up here. So I'm sending a CQ there. So those were the first systems. Basically, you had DC current flowing through a wire. Now the next thing that happened after that is people said, well, hold it now. We've got a cable. Maybe we could get more signals on that wire. So that kind of led to the voice frequency telegraph idea. And the idea behind that is you have several tones within the cable bandwidth. Let's say the cable bandwidth was, let's say, anywhere from, you know, a couple of, let's say 10, 100 hertz all the way out to, let's say, I don't know, you could probably go to 10 kilohertz, but typically the voice bandwidth, let's say 300 to 4,000 hertz. So what you would do is you would put in a bunch of tones in there, space them accordingly, and then you would use frequency shift keying on each particular tone. So the idea rapidly took place, and voice frequency telegraphy came about. So then you can get many telegraph signals on making use of the full bandwidth of a wire rather than just a DC current pulsing through. So that's the idea of frequency division multiplexing, where you've got a bunch of signals sitting on top of one another. Fast forward to the first microwave systems. Point-to-point replaced huge long telephone networks. So you could go, let's say, every 30 miles, you could put a microwave station, and that linked telephony across North America. And in the microwave systems, what you would do is you would stack the voice channels one on top of the other. So typically you'd have a 4 kilohertz voice channel. And the first systems are, let's say, 600 channels, and they went up to 960 channels and 1200 channels. And before the advent of fiber optic cables, basically the analog radios, microwave radios, were up to 2,700 channels. So you'd have 2,700 channels of 4 kilohertz. And in that 4 kilohertz, you could stick either a voice signal, or you could have, for instance, voice telegraphy in there. You could have a bunch of data signals in your voice channel. So that's kind of the history of frequency division multiplexing. Now, the key to OFDM is the principle of orthogonality. And the idea of orthogonality is that if you multiply two tones together and you integrate them over a certain interval, then that product, that integral product, definite integral, is 0. So if you think about, let's say, for instance, in Fourier analysis, if you integrate over 0 to 2 pi, let's say if you integrate sine omega t and sine 2 omega t, then those tones are orthogonal. If you have two sines at the same frequency multiplied together, then what happens is you get the cosine of the sum and the difference. So basically, you end up with a DC voltage of 0.5 and a tone at double the frequency. Now, in OFDM, what we do is we pick a specific integral for or specific interval for our integration. So we're going to space our carriers by a frequency spacing, let's say delta f, and that delta f is going to be equal to 1 over the Baud time. So for instance, if you want your particular carrier to carry, let's say, 100 baud, okay, so 1 over 100 would be 10 milliseconds, and you would space your carriers by 100 hertz. So if you do it that way, then you can be assured that the integral, the definite integral is 0. So let's look at a model here. Here's a model that I use for orthogonality testing. So there's one sign, there's a second sign. I multiply them together and I go into an integrator. So there's my integrator. This interval here is going to be the Baud time for that particular carrier. I'm going to integrate over that Baud time. At the end of the Baud time, I'm going to reset the integrator. I'm going to multiply this by 2 divided by the Baud time. The reason I do this is that if you don't multiply by the Baud time, then the product of the definite integration is very, very small. So if you multiply the sine of one frequency by the same frequency, you're going to get a DC voltage of 0.5 coming out of this. You multiply it by 2, you get 1 times TS, and the TS's cancel out. So basically, if you see the same tone in there, you're going to get 1 coming out of here. Now the tone's going to have various amplitudes depending on the I and Q components. So if the I was 4, you'll have 4 coming out of here. So that's why I set it up like that. In the context, I'm going to start off with, let's say, 200 times 300. Okay, so 200 times 300, they're spaced by 100 hertz. Okay, and if I define my Baud time to be 1 over that spacing, in other words 10 milliseconds, then they should be orthogonal. So let's run that and see what happens.
Now I'll just interrupt there to say, if you have no maths and you're not following this, don't worry. Later on, Jeremy gets into the advantages of this and talks about items like, if you run OFDM to transmit high-quality digital audio or pictures or data or whatever, you have to make your mind up to have lots of headroom in your modulator, because the peak to average ratio of transmitting OFDM is much higher than it is normally with speech or music. It's an interesting point. It means that you have to have a very linear modulation. I'll go back to this, but if the maths is too much for you, be patient, listen through. Jeremy comes out with some very interesting stuff with regard to the possible applications of this, including something called sideband interleaving, which really is miraculous. It almost means that you can put twice as much sideband into a half the channel. You'll see what I mean in a minute.
Okay, so there is, what we're seeing here, there's tone 1 at 200 hertz. There's tone 2 at 300 hertz. That's the product of the two tones, and this is the integration. So the integrator starts off, it gets a certain area under the curve. Now this is one cycle, so after 10 milliseconds, which is there, what do you see? Then the integration has gone to 0. Okay, so they're orthogonal. Now let's pick a different tone here. So let's say 200, let's say 275. Okay, so my spacing is 100 hertz, but my tones are not spaced by 100 hertz, they're spaced by 75, so this won't be orthogonal. So if I run this, let's see what happens now. Okay, so there's my 200, there's my 275. Now at the end of that particular cycle, notice that we're sitting up here. This is not 0. So at the end of the next cycle, we're sitting down here when it resets, so we're not at 0. So you can see clearly that these tones are not orthogonal. Okay, so that's the way to test for orthogonality. Let's go back to our blog post here. Okay, now another thing we can look at, so in the blog post here I put in the orthogonality tester. There's the product of 200 and 300. You can see it goes to 0 there, and there's the product of 200 and 275, and you can see that it's not orthogonal. Another way to look at this, if you look at a a QAM signal. In the previous blog post, incidentally, I covered 16 QAM, 32 and 64 QAM. So if you want to go back to the previous blog post, I can show you how you build QAM and the various properties. You might want to do this before you listen to this particular post. But there's a QAM signal, so the main lobe is there. That's the carrier frequency. Now the null, the first null is at 1 over the baud rate. So let's say the baud rate was 100 bauds per second. So this null here would be 100 hertz away from here, or 1 over the baud rate. So if this is 10 milliseconds, that would be 100 hertz. So that's what a QAM signal looks like. Now in OFDM, what we do is we stack the carriers one on top of the other. So there's my first carrier at FC. So what happens is for the second carrier, its first null, if we make the spacing 1 over T baud, its first null is sitting under the peak of this carrier. So basically the spectrums are overlapping, but they're orthogonal, and we'll see that in a minute. We can pull those signals out. So that's the principle of orthogonality. So what I'm doing here in this post is I'm just hypothetically saying, hey, wouldn't it be neat to have an OFDM system for an amateur radio transceiver? So if you look at an amateur radio transceiver, all the digimodes work with the USB interface with, let's say, a single sideband transceiver. So if you look at the USB interface, it goes from 300 to 2700 hertz. Okay, so that's the bandwidth we have to play with. So let's say we stick our OFDM signal in there. Now the center frequency here is going to be 1500, and I've got 2400 hertz to play with. So let's start off and say, hey, let's make an 8-channel OFDM system. Okay, so if I have, let's say I'm using 16 QAM. Okay, that means 16 QAM is 2 to the 4th, gives you 16. So I've got 4 bits per baud. Okay, so 8 channels. I'm going to number them from 0 to 7. Let's say my system bit rate is 9600 bits per second. Now later on we're going to look at, let's say, what's the maximum number of bits? What's the capacity of this USB channel in terms of the Shannon limit? And depending on your signal to noise ratio, something like 12 kilobits per second. So that's the best theoretically you could ever do with anything, with any modulation technique. No matter what you invented, according to Shannon, you're never going to cram through more than, let's say, about 12 kilobits per second. So let's say we say our data rate is 9600 bits per second. We're going to use 16 QAM. And let's say I space my carriers by 300 hertz. So that'll be the baud time. Okay, so my first carrier is going to be at 300, the next one at 600, 900, 1200, 1500, 1800, 2100, and 2400. So those are my carriers. That's my spacing, 300 hertz. Now the baud time, if the spacing is 300 hertz, 1 over that, like 1000 milliseconds divided that is 3.3 milliseconds. So that's the baud time. So for each one of those carriers, if you take 9600 and divide it by 8, you get 1200 bits per second per carrier and 4 bits per baud, so that means my baud rate is 300 hertz. So that works out. So let's look at a Psychos model. So what I've done here is those are my first 4 channels, and those are my next 4 channels. So I've got 8 channels here. I'm adding them all together. Now each one of these channels is a 16, it's a super block. So I open up, let's say, channel 5. This is a super block that gives you 16 QAM. So in my previous post, I discussed how you build this. But basically what I'm doing is each one of these generators, I'm feeding with a random integer generator. This will generate an integer from 0 to 15, okay, because there's 16 levels. It'll go into here. This block gives you the equivalent for each one of these states from 0 to 15. It'll give you an I value and a Q value. That'll be the amplitude of the I component. Excuse me. There'll be 4 different amplitudes and 4 different amplitudes of Q. I think it's -3, -1, 1, and 3, something like that. Okay, and then you multiply that I by cosine and sine by Q. All right, so that's the super block. So those are my 8 channels of 16 QAM. For the simulation, I initially put it in a sideband filter, but I took it out. And the reason being is that this thing's going to add some delay, and it's going to screw up my receiver. I didn't want to do that. So it's in here. I guess in a practical system, you'd want the SSB filter in there, but I just, I bypassed it internally. It's just bypassed right now. So the output goes to a fast Fourier transform spectrum analyzer. scope. I also save my output so I can input it into the receiver later to analyze. So let's run this and see what happens. So what we're seeing here, this is the output. This particular graph here is one of the superblocks, superblock 5, so channel 5. It's just showing you this is the output of the random integer generator, so from 0, various numbers up to 15. And these are the various numbers for I and Q. So you can see I, for instance, it goes from 3, 1, minus 1, 3. So those are the 4 values of I, and the same thing for Q. This here is a spectrum of the OFDM for the A channel. Notice that it's kind of a flat top. There's sort of an industry jargon. They talk about a BART head. You know, Bart Simpson has that kind of crew cut. So that's what they call a BART head. So those are your A channels, and this is the this stuff is, like, say 20 dB down. These are the other products of the spectrum, but that's where your information is. The sideband filter, of course, or your digital filter, can get rid of all of that before you transmit it. And notice that this is the output of the OFDM. Now, one problem with OFDM is it's got if the average value, let's say, is down here, it's got a huge peak to average value. So if you're going to put this OFDM signal into an amplifier, the amplifier has to be very linear.
This is VK3AML with a regular Saturday night live stream. This one courtesy of Jeremy Clark VE3PKC, who's going into the mathematics and the figures and facts behind OFDM. That is the coming method of Hf transmission for data and digital transmission within a 3 kilohertz bandwidth. And I want you to particularly notice what he's saying about modulation quality, linearity. People think that I have a fetish for audio, but one of the reasons I have that fetish for audio is not because I want to transmit high quality audio per se. It's because I want to transmit OFDM. So back to Jeremy Clark.
Because this is the type of signal an amplifier would hate. So typically you'd have an amplifier with a certain gain and you'd back it off quite a bit to make sure it was ultralinear. Okay, so that's how we generate the A-channel OFDM. Let's look at our receiver now. So what we do in the receiver here is we read the, in the transmitter there, I saved the output into a vector called, or a matrix called A. So I'm reading in the matrix A again. So that's basically the signal from the transmitter. And here I'm just looking at channel 5. Okay, so what I'm going to do is I'm going to resurrect my I and Q components. I'm going to multiply this 8-channel signal by omega 5, so the frequency from channel 5, cosine and sine. All the other components when multiplied by this will give you 0 because they're orthogonal. I'm only going to get out channel 5 times channel 5. That'll give me half a volt DC. And in my integrator, remember I said that I had 2 over TS. So I'm going to have, let's say for a 3 volt I signal coming out of here, I'm going to have 3 volts coming out. I'm going to sample and hold that, and that'll be my I signal. So let's run this and see what happens. Okay, so this is my I signal here. This is the output of the integrator before it goes into the sample and hold. So if you expand this here a little bit, you'll see the operation of the sample and hold. Okay, so this is my I signal. It doesn't start till here. There's a delay because I'm waiting till, I'm waiting basically 1 TB before I sample at the end of the period. So there's the output of the integrator. It's building up to certain values, and just before it resets, I sample it. So that's the sample and hold. So if you look at this signal here, I and Q, and compare it to the transmitter, I and Q, you'll see that it's exactly the same thing. So basically that's my receiver then. It works on the principle of orthogonality. I sample and hold and I get back my original signal. All right, now, that's all fine and good. So there we are on the blog post. That's my transmitter, that's my receiver. And there's my resurrected I and Q, and that's the generator integer generator, and you'll see that that's the same as, sorry, that's the transmitter. Down there, there's a receiver, and you'll see that that and that from the receiver are the same as this and this. Now, let's think about this again. This was an 8-channel system. Now, the problem with the 8-channel system was the baud time was 3.3 milliseconds. Now, that's not, if you're talking about, let's consider, we're talking about an SSB transceiver for ham use. Let's consider we've got the best possible skip off the F2 layer. Let's say the virtual height of the F2 layer is 325 kilometers. So what's the maximum distance we can go? Well, let's say we have a takeoff angle of 0 degrees. The maximum propagation distance is 1,121 kilometers for one single hop. Sorry, that's the maximum distance between the 2 points. The maximum propagation distance, since you're going at 325 kilometers up, is 1320 kilometers. So if you work that out, it's 4.4 milliseconds. So basically one hop on the F2 path is 4.4 milliseconds. But if we had an 8-channel system, hold it, that's only 3.3 milliseconds. So what happens if there's any multipaths? It's going to completely screw up your signal and you won't be able to regenerate it. So what we really want to do is we want to go for a higher channel system where we can increase our baud time. So for instance, let's say we went to 150 baud instead of 300 baud. That would mean we would have a baud time of 6.7 milliseconds, but we'd have to have a 16-channel system. If we went down to 18.75 baud, look at this, we could have 53.3 milliseconds, so it's much bigger than 4.4 milliseconds. And basically we could have a 128-channel 16 QAM system. So what I've done here is, since this is a 128 channel, this would be very difficult to build in Psychos. You could make many super blocks and you could build it. But if you look in the literature, reference 3 and 4, reference 3 is my favorite textbook by Professor Couch. He's at Florida State University. And reference 4 is another great book by Simon Haykin at McMaster University. And they have detailed descriptions in there of OFDM and how you can use the inverse Fourier, fast Fourier transform to build an OFDM signal. So that's a much more efficient way, and that's how they basically do it these days, is they build the OFDM using the inverse Fourier. In figures 11 and 12, what I've got is the GNU radio companion model for 128 channel system. So I'm using the OFDM modulator, and I'm using a random source here, and I'm going into basically an FFT just to show you what it looks like. So this plot here is the random data going into the OFDM modulator. You can set up the OFDM modulator for different types of modulation on each channel. I've set it up for 16 QAM, and I've set it up for 128 channels. So what you see here is you see a spectrum going from minus 1.2 to 1.2 kilohertz. So that's basically a bandwidth of 2.4 kilohertz. And you've got the BART head here, and you've got 128 channels. So what you would do with this particular spectrum, this IFFT spectrum, is you just knock it up to the middle of your SSB bandwidth. So this thing right now is centered at 0 hertz. So using DSP, you would translate this spectrum up to 1500 hertz. So you'd be 1.2 kilohertz down and 1.2 kilohertz up to make use of the full 2400 hertz bandwidth within the SSB USB. So that basically what we've seen then in this particular post is we looked at OFDM, the history, the principle of orthogonality, a simple 8-channel system for a hypothetical ham radio implementation, and how that would probably not be good because of the baud time being too small, and how you could increase the baud time to a respectable value by using more channels.
And my thanks to Jeremy Clark VE3PKC for allowing me to use that. I actually dropped him an email, and he seemed more than willing to let me use that. I know that it'll go over the heads of people who haven't the background in maths or in communications engineering, talking about things like Fourier transforms and all that sort of stuff. But be aware, this is the coming form of modulation, and in some way most of us who are into ham radio are going to encounter this. If only as users, at least you'll understand that using orthogonal frequency division multiplex, multi-subcarrier technique, you have to keep the levels well within the ability of the communication system to transmit. And one of the worst things you can do is to put in too much modulation. We'll move on now to a related topic, and that is developments in ionospheric monitoring, ionospheric prediction. And again, I've written to Phil Erickson, W1PJE of Massachusetts. He's the head of Atmospheric and Geospace Sciences Group at the Haystack Observatory, run by M.I.T, the Haystack Ionospheric Observatory. Phil Erickson seemed also very willing to make usage of this for our Saturday sessions, and asked me to report back to him as to what the reaction would be. It'll be interesting to see what comments we get on this afterwards. This is a little bit more user-friendly. This talk doesn't go into the maths quite so much, and the results Phil can show in a visual way much better than we could in talking about orthogonality and all that that implies. So let's have Phil Erickson's talk. This was delivered to an ARRL meeting in 2017. 2017 ARRL New England meeting, Science of Hf Propagation with Phil Erickson, W1PJE.
Hi everybody. So welcome to talk number 2 in the propagation track. I wanted to thank Tom for doing a really excellent job in giving a whole lot of basics, which made my life a lot easier for this talk so that I didn't have to go through those basics. Just by way of introduction, I'm Phil Erickson, as you see up on the screen. I'm an assistant director at a place called M.I.T. Haystack Observatory, which is on the Westford-Groton town line. And we do research into the near-Earth space environment, including the ionosphere and its variations. And we study the things that make you guys pull your hair out. I like to study storms. And storms, of course, as we heard from Tom, are not always the best thing for propagation. But I hope, in addition to showing you some more, I think the goal of my talk, really, it says the science of Hf propagation. My goal is to lift the lid a little bit and go into a little more depth in some of the things that Tom talked about, specifically having to do with Hf propagation, and then to show you a few of the hairs on the dog, the things that, in fact, are the real natural environment where the ionosphere doesn't look like a nice uniform mirror, for example. And they're really fascinating. And in the process of this, I want to mention that every person in this room actually is capable of helping us with scientific research. And we have an initiative going that will actually allow you to contribute to that, so I will talk a little bit about that as well. That will set up Joe Dukevich later, who will talk about a particular experiment he did on his own, which has turned out to generate some interesting science. So that's my goal today. I have to really thank all these individuals. These are my colleagues and my friends. Some of them are professors at various institutions across the country and, in fact, the world. The amateur radio community is a wonderful community. In fact, in preparing for this talk, I ended up getting an email from a fellow in Portugal who sent me a very nice audio file for a flare effect that I'm about to send you. He just had it lying around. And then my friends from back at Haystack and in the Neshoba Valley Amateur Radio Club, which is my home club, which is right next door to us up at Haystack. So thanks to all these people. This is my outline, a tiny, tiny bit about my background. I'm a amateur, but just to let you know why I ended up getting into space physics as a field, it has to do with what you guys are all interested in. And then I'll talk a little bit more about the ionosphere, which is what Tom talked about in the first hour. And I'll talk a little bit more about the science of Hf propagation, a few of the principles that are underlying some of these propagation models and rules of thumb that Tom talked about. and a couple of nice movies of the variables that the real ionosphere puts into you for NVIS, near vertical incidence skywave, and also oblique propagation. A little bit about that initiative that I talk about, where we're hoping to have amateurs like me and like yourselves contribute to our scientific research. And then this week, I couldn't have arranged this better. The ionosphere and the sun got really crazy. And in fact, I'm still running a large radar system to measure the effects as we speak here. About an hour before this talk, I was checking on our radar, which I'll show you in a minute. So I'll talk about a couple of interesting things and just show you what that does, in fact, to Hf propagation, so that maybe when you're sitting at the radio and something funny happens, you won't think it's just you. This is where I started. This is a Hallicrafter's SX110. This is what I used when I was 12 years old. Those of you who are familiar with bottles, as the British will call them, will recognize some of those particular elements. This is me shortwave listening to this funny woman from Vatican Radio who came on for a half an hour every week in English, in between talking in Italian. So it started there. And it started with restoring this 10S567, which is a 1941 extremely nice sounding shortwave set. Not exactly put it in your pocket. And it just kept going from there. And I ended up here. This is where I work. This is M.I.T. Haystack Observatory. This is our complex up in Westford, Massachusetts. And we've been here since 1956. And these are the instruments that I work with. We do radio astronomy. I do atmospheric science, which includes ionospheric research. We do space surveillance. This is where Lincoln Laboratory helps keep track of the objects in near-Earth space. We're all doing radio science in one form or another. And then we come out and interface with many communities. And in my case, since this is my hobby as well as my vocation, that means I get to do even more interesting things. These are my antennas. These are at UHF frequency. This is a 150-foot fully steerable antenna. There were 4 of them made. There are 2 of them left. This is one of them. And this is a 68-meter or 220-foot vertical reflector that just points up. I won't talk in this talk about the particular radar techniques that I use to do this, nor will I give this talk exclusively about space weather. We could do that in another year. But just to tell you that we work with big stuff. But for these purposes, you have to go all the way back to the beginning. If you're thinking about Hf propagation, what I showed you was UHF frequencies. Now let's go back down to 1 to, say, 30 megahertz. There's Marconi up there. And I understand, if those of you who are history buffs, there is a very large debate as to whether Marconi really did this, really made the first transatlantic contact. My assertion to you is that it doesn't honestly matter whether he did it or not. It triggered so many people to look at this particular part of the spectrum, and in fact was the beginning of the signals intelligence community, because SIGINT people started to show up and in fact went to England to monitor whether he was actually doing this or not. So in some sense, it doesn't matter. But this was his transmitter. That's a monopole antenna there and a spark gap. There's his particular drawing of his particular gear. And there he is hauling a kite up in St. John's, Newfoundland. And he claims he received a couple of dashes from there to Cornwall, England, and Galway, Ireland, back in 1901. Now, that's obviously not local propagation. You cannot see England from where he was. So something must have been going on. And so then this lovely fellow here in the nice vest with the pocket watch is Oliver Heaviside. This is a British physicist. And he, in fact, said, well, he started to think about the things that Tom, in fact, talked about. There was not only a ground wave, because, well, England you can't see from Newfoundland, but there must have been some kind of layer up in the sky that was reflecting those signals and allowing them to propagate geometrically over long distances. And in fact, that was called the Kennelly-Heaviside layer. Kennelly was another physicist. And those of you who like musicals, that's the same Heaviside layer that Andrew Lloyd Webber borrowed for Cats. Okay? I don't take credit for that. But he named it something. He named it the E region. E stands for electrified, because he figured there must have been some kind of free charges up there that were in fact reflecting the signal. There was a very large resistance to this by physicists. The reason was, anybody who's been in a pool and has been underwater and has looked up at the surface of the water, sometimes you notice that it looks like a mirror. You can't even see out of the surface of the water. That's total internal reflection. That's what must have been happening at this boundary. But that means that the refractive index in the ionosphere, the speed, must have been less than the refractive index in the atmosphere. And because that's what's happening when you're down under the water and you're looking up into the air. But the problem was that we knew that the speed of radio was already the speed of light. So how can anything be faster than the speed of light? So nobody believed him for a while. And it turned out it took until Sir Edward Appleton, who got the 1947 Nobel Prize for this discovery, who discovered that there were two kinds of velocities. There was a phase velocity, which is the wave front. If you count the wave fronts moving along, the undergraduate physics, you do this. That actually can be greater than the speed of light, but the group velocity, that's where the packets travel, that's the information in your voice traveling on the RF carrier, have to be less than the speed of light. This is the first guy to work it out. You use this every time you make a long-distance contact. You could not make a long-distance contact unless you had total internal reflection, or a place where the apparent speed of the wave appears to be violating Einstein and going faster than the speed of light. So there's even a little bit of physics every time you turn on your radio, just buried right there. And there's plenty of little videos on YouTube about this, but here, for example, are two waves. The red one is moving slower than the blue one, and then you can watch the packets coming back and forth. And if you trace the speed of one of those little top wave fronts, you will find that it is moving slower in this case than this packet. So phase velocity can be different than group velocity. All of that was to explain why this funny radio thing that you guys use every time you turn on your radio, why was that happening? So we've discovered that there's a conducting layer, as Tom said, of something that's actually refracting, not necessarily hard reflecting, but it's got a different index of refraction, and in fact it's a gradual change in index of refraction, so it's actually bending this ray over. Now, that's the ionosphere, but the ionosphere has a very large relation to our atmosphere, the bunch of neutral gas that's gravitationally and rotationally trapped around our planet. So we have a neutral atmosphere, and this is where we live in the troposphere. And then if you go up, 20, 30 miles, you're in the stratosphere, and then you're into the mesosphere, which is the coldest place on the planet. It's like minus 100 and something Celsius up here. And then you get up to what we call the thermosphere. It's very hard to see. Those are names for the neutral part of the atmosphere. The sun has a lot of extreme ultraviolet radiation. Some of that, again, as Tom mentioned, knocks electrons off these neutrals and converts them to positive ions and negative electrons, which are sort of free. They can go more or less where they want to, although they don't want to get a huge distance away from their huge positive cousins. So in addition to the neutral atmosphere, as those EUV photons come in, they're going to ionize at different rates. And in fact, the deeper in the atmosphere you get, the less of the EUV light is left. And what you end up with is layers, and this chart was already shown. So the neutral atmosphere plus the sun's ultraviolet rays is the source for the ionosphere that we all use to do long-distance communications. And these have layers. Notice the E. I've already talked about the E layer. The E is for electrified, and that goes all the way back to Heaviside in the 1920s. And then there's the F layer. F is one more than E. I'm not making that up.
And you're listening to VK3 Alpha Mike Lima on 147.475 megahertz NBFM. We're simultaneously live streaming on YouTube with the visuals for this lecture. So if you want to look in on the lecture, see the visuals, please Google VK3AML 18 June 2022. That's Google the phrase VK3AML 18 June 2022, or look for the Oz Radio Historian channel, one word, AUSRADIOHISTORIAN, Oz Radio Historian, one word, and go for the latest video, which will be this live stream. Back to Phil Erickson, Dr. Phil Erickson, W1PJE.
It's how it was named. And then eventually people realized that there were two different chemical compositions for the ions. So that we have the F1, which is mostly molecular ions, and the F2 layer, which is mostly O+. And then there's the D region. D is one less than E. Again, I am not making that up. There is no C, B, and A mostly. You may see textbook things on the web that say there is a C, B, and A. Nothing that I know about really talks about that. So honestly, where the electron concentration is significant, during the day there's some in the D region, which is a pesky problem for anybody trying to, because this is a very highly attenuating layer for radio waves. But during the day you have the E layer, and then you have the F layer up here. This is a log scale, by the way. Remember, it's 10 times as many electrons per centimeter cubed from here to there. So this is a pretty big peak compared to this. And then at night, when the sun turns off, recombination starts to work. The neutrals say, hey, I want those the ions say, I want the electrons back, and I want to convert myself back into neutrals. So the E layer actually goes away fairly quickly, except for these funny things called sporadic E, which Joe will talk about. The D layer is more or less gone where the sun is not. And then the F layer actually sometimes hangs around all night long. This is the reason why long-distance propagation occurs differently at night during the day. And I can tell you why that hangs around all night. Well, the problem was first formulated in the 1930s and the 1940s. We still don't know exactly why. We are still researching that because it's very complicated. It has to do not only with what's locally produced, but what's transported from various places. So, but that is one of the reasons why the propagations change from day to night. So there's, again, the vertical structure. Here's the E region, mostly made of molecular ions and free electrons. There's the F region, mostly made of oxygen ions and electrons. And then in the top side above here, it starts to get light. You get helium ions and hydrogen ions because the atmosphere gradually gets lighter. Only the lighter elements remain. The rest of it is sorted out by mass. And the D region is very highly collisional, so in fact, it doesn't like to pass radio waves through unmolested. It actually robs energy from them. So when it's around, it's a really sharp attenuator, as we'll see. And then we'll talk about ionosons in a little bit. But this is the vertical profile of a typical electron density profile if you just look straight up. This is something that we directly measure at Haystack Observatory. This is using an esoteric technique called Thomson scatter radar that I, again, won't talk about today, but treat this as an experimental measurement of the electron density as a function of altitude. This is about 150 kilometers. This is about 600 kilometers. The space station is somewhere in here, and the shuttle used to fly around there when it was in stable orbit. And this is time, and we do everything in universal time here because I communicate with colleagues all over the world, and I don't want to figure out what local time it is there, or whether Kazakhstan has, daylight savings time or not. So this is universal time, so you can tell where sunrise is. So this is the beginning of the day. This is local noon time. This is dusk, and then you can wrap your eye around to here, and then here is the night. So very quickly you can see that down here, and toward the E region, notice the E region's around during the day and then it goes away at night, but the F region does not. You'll also notice that that is not at all a smooth profile. And there is variability in this day to day, and that's called space weather. Part of what we do for study is we study the variations in this, just like the lower atmosphere people study weather to make meteorological forecasts. We're trying to make space weather forecasts, but first we have to understand the physics. So this is what the ionosphere is looking like if you just look straight up. This is a map of the entire planet over 24 hours. I'm sorry about the little bit of flickering. If you're looking up and then putting a pixel there, and then you're just doing that as a function of distance. This is actually calculated using GPS receivers, the same receivers that scientific grade are the ones that are in your phone that you navigate with. It turns out that they have the ionosphere embedded in their data. And so this is 24 hours in the life of the upper atmosphere. Nobody lives in the ocean, so the data goes away there. But you can watch the subsolar point. You can tell where it's noon. And you can also see that is not by any means smooth. So what you are propagating through when you get down to your radio and you tune it up to 40 meters and you're making a long distance contact, you're actually doing highly refracted signals through this kind of structure. This is all space weather. We're trying to understand how this varies not only in space but in time. And to blow your mind even more, now what I'm going to do is I'm going to take the background off. I'm going to take the background atmosphere off, and I'm just going to look at the perturbations in the atmosphere. And I could watch this essentially all day. Just watch the number of traveling waves go through there. This is not a particularly disturbed period. This is reasonably quiet conditions. There's stuff coming out of the high latitudes here. There's stuff rolling around at mid-latitudes over the continental United States. There are waves going past the magnetic equator. This is a live view calculated every 30 seconds or 1 minute of space weather. This, again, is what your HF signals are propagating through, which is why rules of thumb are rules of thumb. They're great, but don't hold them to that rigidly, okay? But that means that the propagation that you're experiencing any day has this kind of physics embedded in it, if we can only figure out how to get that information and process it, which I'll talk about a little bit later. One of the reasons that is still complicated is the ionosphere is strongly magnetized. We live around a planet that has a very strong magnetic field. That means that the electrons they can't just go anywhere. In addition to gravity and collisions at certain altitudes, they have to pay attention to where the magnetic field is going. Because to first order, the electrons have to actually gyrate around the magnetic field. That's gyromotion. These are other physical invariants. And as Tom showed you, we have a complicated magnetic field structure around our planet. And so imagine all these electrons that really want to stay stuck to these magnetic field lines unless you shove them so hard that they pull off it. And so study of this phenomena happened again in the first half of the 20th century. How do you predict propagation when you got a magnetic field that in fact keeps tilting on you? Because remember that the magnetic field is not the same angle like at the polar cap, where it's pointing into the ground, as it is at the equator, where it's parallel to the ground, or here, where I happen to know the dip angle is about 68 degrees. If you looked up, there'd be an imaginary magnetic field line stuck up at about 68 degrees coming through this room. So this adds complexity to the propagation predictions, which is why I thought the advice was very good, is that start with the rules of thumb and then let some of the propagation predictors do the hard work for you, because this system is really complicated. And frankly, we're kind of in an embryonic stage for even propagation prediction compared to what, for example, the weather models can do. So your activities, your contacts are actually, again, at the forefront of trying to understand this very large and very interesting coupled system. The other interesting thing about this is that look where the magnetic field lines go. This comes out of the northern hemisphere, goes all the way across the equator, and goes to the southern hemisphere. This is an inherently non-local system. Conditions here, we've done research where we can tell that conditions here affect conditions off the southern tip of Tierra del Fuego in South America, because that's where the magnetic field line ends up that goes through this room. It's a really challenging problem. And we are very data starved because nobody lives out here. Yet. So the magnetic field, to put a little more subtlety to what the propagation information that Tom presented, the magnetic field has a large effect on propagation. If I put a transmitter right here, and I didn't have any magnetic field, it would take the green line from transmitter to, say, a receiver here. This is latitude and this is longitude. If I throw the magnetic field line in, as soon as I enter sort of the ionosphere, the signal actually splits into two directions. One of them is called the ordinary wave, that's the blue, and one of them is called the extraordinary wave, that's called the purple. And sometimes they end up in the same spot and sometimes they don't. This is just like a birefringent crystal, for those of you who ever looked at one. If you go to rock shows, they're often there, and you can put a piece of text there and the text sort of blurs into two, because it's got two different refractive indices depending on what axis you look at. The ionosphere is like that. So throw in a variable magnetic field, and that complicates your propagation predictions, which just means it's interesting. I mean, if things always propagated the same every time, if you could always talk to your friend in Patagonia, predictably, this would be a lot more boring, frankly. And if there was no solar cycle and it was the same every single day, depending on how much you like your friend in Patagonia. I mean, you know, that might be less thing. Oh yeah, sure.
Why did they define it as ordinary?
Sorry, say that one more time.
Why did they call it ordinary?
Okay. It turns out that when you work, the question is, why do they call it ordinary and why do they call it extraordinary? To make the answer very short, if you look at the physics of what happens when you enter a place that has a significant magnetic field and has charges around, there are two principal propagation directions. One of them goes along the magnetic field, and one of them goes perpendicular to it. They called the along the magnetic field direction ordinary, and they called the perpendicular to the magnetic field direction extraordinary. It's naming. Like, why did they call it the D, E, and F regions? They could have said propagation mode A and B, but
Does it have anything to do with the splitting right-handed, left-handed rotation?
that's another whole talk, but you're launching a polarization from here, and actually when it enters the bottom of the ionosphere, some of that energy is going into one mode and some of the other mode, and then it's reassembling itself when it gets to the other side. So there would be a difference if you excited it with linear polarization versus circular polarization. We can talk offline about that. But the magnetic field does have an effect on the propagation. So all of this is very complicated. So let's go back to how you'd measure this thing. This is Gregory Bright and Merle Tuve. He was instrumental in founding the Naval Research Laboratory in Washington. They actually came up with the Ionosond in 1926. If you look at their dates, you realize that he was 27 when he did that, and he was 25. Sorry. I feel like I should hurry up and do something significant. So Tom talked about it. What you're essentially doing is you want to measure the ionosphere now, so you don't want to necessarily have a ray propagate all the way over to the other corner there and not necessarily know where it came from. I want to actually measure what that ionospheric profile is to put in my propagation model. So I deliberately construct an antenna which goes straight up, and I'm going to look for the point where I get total internal reflection, and then the wave bounces back to me. That's going to happen at a certain delay, and I can convert that into an altitude, and then I change the frequency, and it's going to bounce at a different altitude. And at some point, I'm going to have a frequency that's so high that it's above the critical frequency, and I'm never going to get it back. It's just going to go straight on through the atmosphere, and I never get anything back. And I'm probing the ionosphere by doing that, and that's what these guys came up with. And they did it in the 1920s. This is the principle. You can either, and in fact, there's a couple of different kinds of ionosondes. You can either send the thing straight on up and bounce it straight back, and then when you think you know what you're doing and you get some confidence, you try oblique ionograms, where you actually go like this and you bounce it, and then you try to figure out what the altitude of the reflecting layer was. And this is how they worked out all those different layers, by doing these kinds of experiments at HF frequencies. So in some sense, if you sit there with your mic and you have the PTT key and you go click, and you could do it with about, say, a millisecond of on and off, you'd be doing an ionosonde experiment if you had calibrated the rest of your system. And we could talk about that. Here's some examples of ionosondes. This is in Ethiopia. This is up in the Falkland Islands. This is at Sonderstrom in the Western Fjord in Greenland, Ascension, Bear Lake in Utah. There's one at the foot of the hill at Haystack Observatory. A lot of these were built by UMass Lowell, which Tom had put up the UMass Lowell Digisonde. That's digital ionosonde. So you can see the typical transmitting arrays involved. They're designed to go pretty much straight up, and then they usually have directional receive arrays, so they can tell when some of the waves are not necessarily bouncing up, but maybe doing a little bit of off vertical propagation. They're typically made on a 1 minute to 5 minute cadence, 24 hours a day, 7 days a week.
These are official measurement stations around the
That's right. There's about 100 of them-ish at the moment. We would like about 50,000 of them. I can tell you something, that I have a colleague who used to be at Haystack, who is now a professor in Norway. He made, these typical power levels for these things are typically a few hundred watts. Okay, so within the RF amplifier, power levels that you guys are used to. My colleague did an ionogram with 3 milliwatts, which is about one AA battery. If you process it right and you use advanced coding techniques, you can actually make a very, very low power ionosonde. Then we could afford to put 100,000 of them out. As it is, these are about $250,000 a piece, which that buys you a lot of Ameritrons. So how does this work? It turns out that unfortunately it's not as simple as that, because the ray doesn't just go up, 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 turn right around and come back down. It actually slows down just before it turns around. So the amount of delay in time you have to interpret. So you get these funny scooped things on the ionograms, and then you have to invert them to figure out what was the electron density that gave me this kind of very complicated echo as a function of frequency. And so there's a whole art that's been built up over decades to do that. And so, for example, this is a classic ionogram. Here's the frequency they were transmitting at, 1 to 19 megahertz. Here's the virtual height or equivalent delay from when they transmitted to when they received. So they send a pulse, wait, come back. And here are these traces. You'll notice, by the way, that there's more than one of them. This is single hop. This is double hop. So this is when the signal went up and then went up, back, up, back. And you'll notice that there's a cutoff beyond which I don't get anything more. That should remind you of this FOF2. So in fact, then magic happens and people assign various frequencies to it. We have FOF2 right here, but there are other things where I'm trying to get the shape of the other layers. But you get to do fun things like trying to find cusps in this particular thing. And then our friends sporadic E that Joe will be talking about in the next lecture come along and blanket and sometimes cover up some of these and make life interesting. But there are professionals who are dedicated to doing this kind of interpretation. I pulled this off the Millstone Hill Digison last night. So this is just, for example, an analyzed modern ionogram. Somebody actually fits a curve to this. They then have a model of how the ray turns around. And this is what they end up producing, which is the equivalent electron density profile. That's what I, as a scientist, or somebody who's doing a propagation measurement, wants to know. You'll notice that there's a dashed line here. The ionosonde on the ground cannot measure anywhere above here, because how can I measure a layer here when this layer is reflecting all the energy back? So in fact, ionosondes are blind to the top part of the electron density profile. They can only see the bottom side, which if you're standing on the ground and you're trying to propagate like this is more important, but if you're a physicist, you like this. So there have been rare occasions when you take an ionosonde and you bolt it on a satellite and you fly it this way, and so you sound this way. They can't see the bottom. This can't see the top. And they're never in the same place at the same time. Ever. But you can do that. And this is what ionograms used to look like. And aside from just a picture, I actually have one right here. This is from the thesis work I did down at Arecibo. And they used to come on paper like this. This is carbon paper on the back, and they just run a little arc and burn the line in with a mechanical device that ran this through. And it worked about 10% of the time. But I keep it sentimentally. Before that, they actually did it on 35 millimeter film. They would just take a picture of an averaging oscilloscope, and they would trace these lines by hand and convert them rather than having a computer program. And so they would do things like this. This is the National Bureau of Standards. This is an ionogram. This is a month of FOF2 in January 1946, scaled by hand. I know someone who works at the Finnish Meteorological Institute way up in northern Finland. There was a woman who did this for 45 years, and she was kept employed because they didn't want to change out the human so that the scaling that she used was consistent. She finally had to retire at 80-something. But this is the way it was done. So in fact, we have a very large climatological area. We have more than a century of ionosonde records, several solar cycles worth. And the fun happens when you start to do ionograms that are not completely up and down, but have a little bit of a takeoff angle, say 10, 20 degrees. There's the two ordinary and extraordinary modes, and there's 1 hop, 2 hops, 3 hops, 4 hops. Bounce, 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 bounce. We don't know what this stuff is. It's probably some spacecraft or low-flying aircraft. And you see this sort of hash here. That actually is sea surface scatter. That's actually stuff refracting, bouncing off the waves where the phase gets scrambled a little bit, and coming back to you. So in the last few years, there's a whole series of people who've started using ionograms to look at sea surface variations. because this is long path stuff. If you can figure out where it's refracting to, you can look at the sea over a very large period. So, by the way, there's the AM broadcast band. Speaking of RFI. WBZ doesn't really help these ionograms too much. And so, you get to run ray tracing programs. These are exactly equivalent to the optical ray tracing programs that people use to make Pixar movies, except for now the refractive index is less than 1, as I described. That was the heavy side scratching its head. And you do this, and you basically trace out, you launch rays from your transmitter using, for example, this super darn HF radar network. This is a bunch of, tens of kilowatt class radars that were rayed around the northern pole. And you launch them in different directions, and you basically just have a model ionosphere with a refractive index, and you trace where the rays go. Some of these rays go out and never come back. At some angles, they actually refract over, bounce off the ground, and come back. Some of them do great things like this. They actually come and they go like this. And then you get to interpret what comes back. So, but this is the fundamental ray tracing that actually helps you take your propagation and turn it over into this colored curve, which is what you want, the electron density profile. And to just show you that that actually changes as day goes into night. And what you're watching here is propagation in action, which anybody who's sitting at their radio, this is what's going on. Here we are. That was nighttime. Now sunrise has hit. And now, as Tom said, the bands have changed. Now the low bands are basically not as well used, and the high bands are, and by the way, this is at a fixed frequency. That's at 11 megahertz. It'd be a different one for at different frequencies. So you use this as your ruler to interpret what you're getting back and get back to that electron density profile. Just another example of one of these ray tracers. I like this one because you get 1, 2, 3 hops, and there's actually 4 or 5 that are cut off by the plot. Some of which have these funny chords that do this, some of which, again, leave completely, and they're different at different frequencies. So, but people have thought about this for quite a long time, and they can make these interpretations. And it does have direct impacts, because what are they using to do this? HF frequencies. 80 meters, 40 meters, 15 meters, 20 meters. And that's going to vary, and that tells us a lot about, in fact, the ionosphere. So just to show you a day in the life of the ionosphere, watch this. This is frequency from 1 to 10 megahertz. This is range, and you can just about see the green curve here. It's now nighttime. Actually, can somebody try to hit the lights just for a moment? It's that switch. Yeah, no, the actual switch, on-off switch. All the way to the right. Notice the trace now is not one line, it's a fat line. That's called ionospheric irregularities. That's the ionosphere breaking up into little pieces. And blanketing sporadic E here for a little bit. We get an E layer at about 100 kilometers. It was blocking some of this scatter. And right now, there's probably 2 or 3 different layers that are scattering and blurring themselves into one, I'm not going to charitably call it a mess. You can almost see 2 traces here. So life, even in a vertical ionogram, is complicated because we have a natural environment that's varying from day to night. And this ionogram is different at different spots. Which just means, again, there's a lot of natural variability that everybody gets to enjoy when they're sitting at their radio. Keep the lights off for a moment. And it gets even more interesting with oblique ionograms. Watch this. You can see the 5 hops happening. You can actually see there's another layer that suddenly appeared. Notice that the virtual range the ionosphere is basically moving up and down due to some waves that I showed you in that other TEC plot. Now it's daytime. There's the sea scatter right over here. That's how I know that by that horizontal cutoff, but you notice that's different too. So lots of information buried in here. You can hit the lights on again if you wouldn't mind. Thank you very much. So how do we use this? Well, we have a model that is determined in part from Ionoson data. You predict that, you shoot rays through it from a known transmitter, and then you get a prediction of propagation. And then that comes out in things like VOA cap, which is a model based on all of this data. And that's how you practically use it to predict Hf propagation.
I'll interrupt there to say this is VK3 Alpha Mike Lima streaming on YouTube and transmitting on 147.475. For those listening on VHF, if you want to see the illustrations that go with this lecture by Dr. Phil Erickson, W1PJE, please Google VK3AML 18 June 2022. That's VK3AML 18 June 2022. Or look for my YouTube channel, Oz Radio Historian, AUSRADIOHISTORIAN, Oz Radio Historian. Back to Dr. Phil Erickson.
Knowing what you know about the refractive index of the ionosphere, and that's the science behind what we're doing. And this has already been shown, but this is nice because it's on the web. I don't have to install a piece of software. I can just run this off the web. This was originally developed for Voice of America for their shortwave broadcast purposes to make sure that they were covering different areas of the planet at different times. You can see the gray line here. You can see where it's night, where it's day. This, you get circuit reliability charts. You can get, I don't know, 1,000 different kinds of plots out of this one. One of them is, which I'll show you in a moment, one of them is, hey, for say 11 meters, as a function of time, what's the probability that I can actually use that frequency? That has to do, you take the maximum usable frequency, you put it in your model, and you do that calculation. My colleague Bill Lyles wanted me to point out one important thing, is that we've been talking about, you will see that the ionosons, okay, tell you what a maximum usable frequency is. That's a measured value that says, hey, what frequency did I not get the signal back? The models have a different interpretation of that. That's actually a 50% probability that you can actually propagate at that frequency. It's not 100%. So people run into the things where they run this model and they say, hey, I think things are okay, but I couldn't make the link happen. That's because if it says that you're near the edge, 50% of the time you can't close the link. So it's just something to remember when you're looking at data versus models when you're trying to predict if I should use a particular band. Now, you could go and do the first principles physics like I just talked about and spend 5 decades replicating what everybody else has done, or you could go to this website. I'll leave that to you to determine which one you want to do. This takes a lot of skill to interpret, though, I will say. That this is a lot of information. I would start with what Tom said as a much, much better rule of thumb. Get yourself comfortable with that. And then you can start interpreting some of these graphs a little bit better. And there is some documentation about that.
Do you think Qam does a good job of incorporating all this stuff you've been talking about?
Oh, yeah. So the question is, how well does this model incorporate it? As well as any empirical model is where I've washed out a lot of the data by averaging a whole ton of stuff. So this is the difference between climate and weather. This is the climate. This is me looking at the forecast and saying, on average, it's going to be 56 degrees today. Weather is what actually happened. So weather is on top of climate. We have good climatological models. We have extremely poor weather models. So that's the space weather part. We're still data starved. So but as a climatological model, it's not bad. So we're data starved. Anybody here run into something called the reverse beacon network? Does that ring any bells with anyone? Okay, a few people. These are automated beacons that are sitting at particular frequencies, and there are other people who are listening for those frequencies, and there's a computer back of it. When you hear a particular link happen, the call sign and the parameters get uploaded to this fairly large database. And it's a volunteer network. There's about 130 different stations. They're not all plotted right here. And there's data back to 2009. And these are amateur radio operators, just like you and me.
And speaking of amateur radio operators, this is VK3AML. In 15 minutes, just past 11 p.m, we'll be opening up for QSOs on 147.475. Back to Phil Erickson and talking about ionospheric prediction.
Who have set up one of these stations. There are other networks. There's WhisperNet. Anybody play with Whisper? Weak signal propagation reporter, right? Thanks to the clever Joe Taylor, whom some of you may know, K1JT got the Nobel Prize for discovering pulsars with Russell Taylor in 1974. We're just very fortunate that he's interested in this subject and continuing to contribute. Look at the data. There's 1 billion of these reports just in the last few years. This is a lot of data. This is sort of big data that you hear. It is not a traditional experiment. I know where the ray started and where it ended, but I have to sort of try to understand what happened to it when it went there. And we in the scientific community are just beginning to come to terms with how we analyze this. So that's where you come in. There is a group that has been started in the last year. This is a bunch of us at Dayton, or Xenia, excuse me. They made us all wear lab coats. That's the white.
Should be put away.
Yeah, well, yes, I was thinking about wearing it today, but I didn't want to do that. And this is three, including Nathaniel Frizzell, W2NAF, who is the leader of this, who is a professor at New Jersey Institute of Technology. This is at the American Geophysical Union scientific meeting in last fall in San Francisco. The objectives are to connect professional researchers like me, some of whom are also amateur radio operators, with you, the community. Because you have large amounts of data that has the ionosphere buried in it because of these fundamental propagation properties. But we need an organizing principle. So we have a group that's hamsci.org. There's the URLs down on the bottom. And in fact, anybody participate in this? Some of you did. This is the Solar Eclipse QSO party. Anybody not hear that we had a solar eclipse on August 21st? I think the answer would be probably you heard about it. It was a contest that was come up with specifically to generate more data on eclipse passage. And I'll show you something about the eclipse to end this talk. Look at the data sources. I just showed them to you, along with participant-submitted logs. You have your log in Cabrillo format or whatever, and you upload it to there, and there's instructions on how to do that if you were operating, and we can start to make propagation sense of it. So the amateur radio community can directly contribute to science. We're crowdsourcing it, if you will. So I'm going to end here, since I've lifted the lid a little bit, by just showing you a couple of strange things that we do not understand, some of which happened this week, in fact, that we can study with your help. One of them is the solar flare. Remember, as Tom said, this is the prompt amount of ultraviolet radiation which is flying at the speed of light. It takes about 9 minutes to get from the sun to the Earth if you calculate speed and the speed of light. That's not a coronal mass ejection, as Tom pointed out. I just want to make that clear. Flares don't always correlate with CMEs. Coronal mass ejections are actual bulk moving material at about 1 million miles an hour, and that takes usually a day to 3 days to get here. We're talking about a solar flare, a really prompt flash, which basically creates a very prompt amount of ionization. Effects, these are effects, we just don't sample this well enough yet, and that's kind of where propagation can come in. This was the flare from about 3 days ago. Here it is 9 UT, so this is about 5 in the morning here, just before dawn. There was an X2 class flare, and I was up early and sitting at my computer. This is the GOES operational satellite, again, the weather satellite. I saw this and I said, really? Oh, this is really great. And then that happened. Remember, this is a logarithmic scale. And by the way, there is no scale above X. The largest flare was an X28. Yes? Oh, okay. He's asking what the worst conditions were kind of ever. Right. We've been waiting for something called, for example, the community for space weather, if you gauge how bad it can get. Okay. There's something called the Carrington Event, which happened in 1859, right at the beginning of the telegraph era. The Carrington Event was still the largest solar flare ever recorded for the past 500 years. In July 2012, we missed having another Carrington Event by about 3 days. We were actually 3 days too wrong in the orbit. And you can imagine how many satellites and cell phones were around in 1859 compared with now. In 1859, when that flare happened, telegraph stations caught on fire and burned down, killed a few people. There was enough current flowing on the telegraph lines that they disconnected their batteries and ran on the current from the solar wind for about 2 hours. They were sending messages, and then they're very New England people, and one of them says, the current's kind of waning. Should I hook my battery back up? Yeah. So it can get very bad, but the question is that the sun is a chaotic, unpredictable object. So we're trying to see if we can figure out what would happen.
Is that basically NEMP?
It's an electromagnetic very prompt pulse, but it's in ultraviolet light. It's not at radio frequency, so it's a little different. The best conditions are, you ask about the best conditions. So he's asking what the best conditions are. Well, the best conditions would be, say, the quietest ionosphere you can think of, things where the sun is the quietest. Tom put up a plot of the last 2 or 3 solar cycles. I was at a geophysical meeting. The last solar cycle was 13 years long instead of 11. It was actually 2 years longer on the end than we thought it was. And in year 11 and year 12, we had these sessions that said, what happens if the sun just turns off? There have been periods in the sun's history, prehistory, where the sun was off for about 300 years, which means that you guys would have great propagation and would never have to worry about solar events. Who knows? That's why solar cycle to solar cycle, we still don't know a lot about even predicting that variability. So we need your help to observe it. So this is the solar flare that happened just this week. I put that up. Remember D-layer absorption? When the solar flare happens, it penetrates so deep into the atmosphere that it creates another D-layer, a really intense one that is unfortunately really, really absorptive for the radio waves. And so I like this movie. This is a movie generated by NOAA, and this is going to be about 1 minute cadence, and this is for the period of time of those 2 solar flares. This is the place where it's noon on the planet, and this is the place where it's sunset, and I'm just going to run the movie. The color you see is the highest frequency that got at least 1 dB of absorption. That's just their calibrator. So when this thing goes from blue to red, pretty much all the HF bands are going to be fairly wiped out. Watch. That's flare number 1. That's not the big one. And you can watch it decay. This is the time. So here's 10 UTC. So the first flare was at 9 or so UTC. Here it is coming along, relaxing. This was me at my table drinking my tea, thinking, okay, we're in good shape. Until that happened. The entire sunlit side of the planet had some sort of effect, including here in Massachusetts. And you can see the recovery time. It actually takes a couple hours for mid-latitudes to recover. And what Tom was saying is that this plot is really screwed up. Don't even look at this, because you notice all of this red at the polar cap. That's because we had something else going on called a Proton Event. And that's been going on for days and days and days and days. So basically, any HF communications, if you're flying a transatlantic airliner and you're going over the poles, don't work at all. So this has been an extraordinary week. But I wanted to direct your attention to this solar flare. Here's what an ionoson saw. So this is a little different kind of ionoson. This is a day in the life of ionoson. This is frequency in this direction. This is time. And the color is sort of strength of the signal. This is a typical day. This is a no-flare day. Here is the nighttime ionosphere. Here's the sun coming up, and there's FOF2 coming up, and you can see there's some structure in there. And now I'm going to show you the day of the flare. Bye-bye. The entire day, there was nothing. That's the effect that the D region absorption can provide you. So if you turn on your radio and suddenly you can't hear anybody, you should look to see whether there was a flare. And in fact, this is Jose Nunes, who was in Portugal. He has a recording of when this happened. He was in the CQ Worldwide CW contest back in November 2000, and he was in Aruba. And so I'm going to try to play this for you, and I'm not going to play the whole thing. He had 2 radios. He was doing SO2R, so this is the one you want to pay attention to up here. And I'm just going to hold the microphone up. Okay, so it's a little hard to hear, but so he's tuning around, listening to things. And then what happens is all of a sudden, everything goes away. Just totally disappears. The rest of this is him going crazy, turning the dial, figuring out what's wrong with his equipment. Okay? And then a very interesting thing happened. This happens for 7 minutes until the bands gradually recover. This is a 26-minute long recording. You can download it. I highly recommend it. And then the interesting thing happens right around here, which is that suddenly the background noise shoots up like crazy. That's actually solar radio noise. Not only is the band wiped out from D region stuff, but you've got extra radio noise at HF frequencies is now getting through the ionosphere and running into his radios. Try to communicate through that. This is what a flare can do. We don't understand flare effects completely yet. I have the URL, and so when people can get access to the PDF of this talk, and the URL is on the thing, and you can download it. He has also a little description, and being a thorough guy, he even has his logs, so you can even, the contesters are amazing. 21 megahertz, 10 meters, or 15, excuse me. So that's one thing we can study that we don't know anything about. And to close, then there was this eclipse, which I was telling you all about. And this was the eclipse track. Anybody here actually go to see the eclipse? Ah, a few intrepid souls. So sadly, it wasn't totality here in Massachusetts, but it was still a partial eclipse. And my point is that the effects of the eclipse in the ionosphere covered this entire continent. Because it's not just where it's totality, it's where it's partially eclipsed, where the sun is partially covered, the ionizations start to go down. So we had an artificial sunset and a sunrise in the upper atmosphere. This is a scanning picture from our radar before the eclipse and after the eclipse. That's electron density. The density dropped by a factor of 2 during the eclipse passage. This had dramatic effects on HF propagation, and the results are coming in. This was overhead Massachusetts. This is before the eclipse. This is electron density as a function of altitude and time. That's straight overhead here. So the totality didn't go over us, but the part of the shadow did. So just to tell you that eclipses have profound effects on the ionosphere, and they happen much faster than a typical sunset and a sunrise when the sun turns off and back on. They're directly measurable. What happened to HF propagation? The Qam collective is still collecting data, but we're practicing, right, because there's an East Coast eclipse in April 2024. So the more of you that participate, the more we can understand this eclipse, because we know this one is coming. And just on a personal note, you can even do things with this fellow. He's sitting there listening to WWV at 10 megahertz and 15 megahertz and just recording their values on an S meter converted to power as a function of time. There's where the eclipse local max happened, and he went from daytime to nighttime conditions. WWV at 15 megahertz went away for him, and 10 megahertz went up, using nothing more than a shortwave receiver and an S meter. He was here. The total eclipse at the time of that was here. The transmitter at WWV was here. So these are paths that went across through the eclipse part. Using a pencil and paper, we're analyzing this data. I should point out, for purposes, that's my 88-year-old father. Using the shortwave that I used when I was 14. I had fun stringing up the antenna for him beforehand. So, just to conclude, these are words from Dan Baker out of the University of Colorado, that we're still studying space weather. It really is basic research with a high public purpose. I hope I've made the case to you that there's a lot we do not understand about the ionosphere, but that you are collecting data every time you pursue the hobby and turn on the radio that can help us figure this out, because we desperately need more data points. So I hope that you'll consider going to hamsci.org, looking at the ways you can get involved, and staying tuned. And I'm happy to answer any questions. Thank you.
Dr. Phil Erickson, and thanks to him for allowing me to use that rather interesting talk, which indicates how much we do not know about the physics of the ionosphere and HF communication. After 100 years worth of HF communication, there are some things that are just beyond us even now, because of the unpredictability of things like the sun and magnetic fields, which I find rather interesting. I know that this week we've been chipping away, let's say, at the more scientific, more technical side of things than I normally do. I thought it was worthwhile pairing those two talks together, the very highly mathematical talk of Jeremy Clark VE3PKC, to whom thanks for the usage of the talk. I've been in touch by email with both parties, and I was very chuffed that following our streaming of Mike Roth's very interesting talk, Radio History Maxwell to Marconi, last week, that they were prepared to chip in with the usage of their material. So things are looking up. Anyway, it's time to open up for a QSO, as usual, on Saturday nights, hoping that I haven't alienated anybody by the excessive depth, perhaps, and seriousness of this stuff. It can get a bit dry, I suppose, for those who aren't used to scientific documentation or maths or whatever. And next week I'll have rather a lighter subject to do with audio, audio equalization for communication channels, and as restoration for defective audio, including audio from 100 years ago, which I'll show to you by some very practical cases, including Nellie Melba, who recorded, unfortunately, when the recording industry was capable of very much less than it's capable of now. That being said, let's open this up for a QSO. This is VK3AML calling CQ on 147.475 and standing by for any calls.
VK3DLWPG.
I've got VK3CG, and hello Dave, and VK3ZLW, I think it was. I'm just trying to remember the name there. He said flicking back pages. I don't think I've got it there. My embarrassment. I'll hand it over to Dave first, with a pause for any other breakers. VK3ECG and group VK3AML.
VK3 Golf Lima Charlie.
Yeah, VK3AML, VK3ECG, and good evening to VK3ZLW. But I didn't break the squelch here. I will turn the squelch down a little bit and see if I can hear something on the next go around. Fascinating videos tonight, Chris. Thank you very much. I really enjoyed them. Yes, well, I'm not a mathematical engineer type, unlike a couple of my colleagues. But I understand a lot of the sort of the general principles and underlie them, and I must say I do enjoy some of the interesting stuff about forward error correction and extreme low power communication. So fascinating stuff, and the multiplexing is certainly something that is fascinating. It's made its way to radio in a number of areas, but mostly in terms of narrowing bandwidth, and of course the ability to use the full bandwidth and then gain the advantage of the increased frequency, audio frequency ranges is fabulous. I suppose it's dependent upon on the various technologies for those who can build that sort of stuff, or for those who just have the sort of simple entry-level software to do the work. It will be certainly interesting to see what happens as people start to become interested in that sort of technology. I don't know, Chris, whether you know what's sort of out there or what might become available in that field for the non-constructors, and what's already out there. Indeed, I don't know much about that. The propagation stuff I really enjoyed. I mean, I'm always fascinated by that, and certainly interested in what were the effects of things like the solar flares and so on. I mean, those massive mass current events where you're going to get huge voltages and currents generated in long wire systems. Of course, it's less so much about long wire systems today and more about the knockout effects of highly sensitive equipment, which can be permanently damaged. Those things, I presume, are still a significant concern. Anyway, back to you. VK3AML in the group, VK3ECG.
3ACZ.
And acknowledging 3ACZ. Okay, Dave. Yeah, it's interesting to contemplate what would happen in today's world if that event of, what was it, 1859? Was to happen today. I mean, the amount of electrical equipment around in 1859, they hadn't even built the overland telegraph at that stage. I think that was still 20 years in the future. Or 15, hang on, 12 years in the future. So with very long lines, as there were later on, I could imagine that causing international havoc, particularly if they knocked out satellite communication. Imagine the number of channels that would go down. It would mean that internet would virtually come to a halt. I'll hand it round. Was it VK3DLW, Graham, or was it VK3ZLW, VK3AML?
Yeah, VK3AML, VK3DLW. G'day there, Chris. And everybody else, Dave and Peter, and 3GLC. I'm not quite sure of your name, but we'll catch up with that. But yeah, no, that was very interesting, Chris, as ever. It takes me back to the communication theory I did back in my university days. I'd have to go back and refresh on all that mathematics to get anywhere near it again, I think. But the interesting, I guess, qualitative thing out of that was I can now understand why when I ventured onto your EasyPal net and started sending, when you started feeding audio to my transceiver here, why I had to wind it back so far because of the peak to average ratio and the need to keep that as linear as possible. And so yes, I kept winding it back. I'd like to get back into that net, but the 3RML computer is problematic. And yeah, the ionospheric thing was interesting. I was involved for 6 years with the Jindalee Operational Radar Network project, and of course that set up a whole network of vertical and oblique ionosons dotted around the countryside, all with the idea of producing data that, after some magic is performed, determines the best operating parameters for the radar, for the HF radar. So yeah, it's all interesting stuff, and I've been running VOA cap here for some years. There's a program that AFREET software puts out called HamCap, which uses VOCAP underlying it, and I've been using it most recently to predict long path propagation to Europe, because that's my most recent antenna construction. And it used to be better. It integrates with a program, also integrates with a program called Ionoprobe, which still runs, but unfortunately some of the NOAA data feeds that provided to it are no longer available. So it's been discontinued as a product. You can't download it anymore, but if you've already got it, it does at least give you sunspot numbers, and it does give you KP values, which you can feed into VOCAP, and it has been predicting long path Europe openings reasonably reliably for me of recent days. Anyway, I'll shoot it back to you, Chris. VK3AML in the group, VK3DLW.
VK3DLW in group VK3AML. Yeah, interesting about Jindalee. I think I might have mentioned previously that I used to almost inhabit a bookstore on the first floor of a building in Flinders Lane back in the 70s, 80s and early 90s, called Book Affair. And they used to buy books, including technical books of considerable depth, by the pound, I believe, from ex-publishers and various other sources, and even academic libraries that were closing in America and elsewhere. And I came across an IEE publication, semi-secret, at the time, this would have been about 1990, 1989, of a conference on HF communication and propagation, and talked about the BBC doing digital tests, but it also talked in considerable depth about Jindalee. And when I bought the book from the counter, the man behind the counter said, oh, that's one of the books that was heading for Saddam Hussein, but the shipment was stopped by federal authorities and the material confiscated. I said, well, how the hell did you get it and sell it to the public? He said, oh, I don't know. They made it available. So it would appear that in peacetime in this country, if the country's not in threat, the security of information is a little bit questionable. I think it probably would be a bit more likely to be the document pulped if it contained anything really sensitive these days, with Ukraine being what it is, China being what it is, and Russia being what they are. Interesting about Ionoprobe too. Perhaps we come back to you on the Jindalee thing just to talk a bit further about that. I've been fascinated to see photographs of the Jindalee arrays in the desert and what you can do with antennas if you've got lots of acreage that's not much value for anything else, basically sand, red sand. Round to Gary. Nice to hear from you, Gary. And how's your week been? VK3GLC and group VK3AML.
VK3AML and the group. Hey. Yeah, very good evening. All well received on the live stream this evening. Actually just checking my radio on the SDR tonight. Just comparing things that I've done before. But yeah, very interesting on the OFDM. Had a bit of experience with it, both with broadcast television and probably more so with DSL, as that form of modulation is quite familiar on both of those modes. So mathematics not so. Mathematics is a fair bit rough. The use and applications thereof, yeah, fairly familiar with those, and that can affect the effectiveness of the aforesaid mentioned mode. Been fairly busy during the week, doing various bits and pieces, working, so I've got a little bit more time to play around, usual end of contract stuff, and getting back into the housework again, which has sort of slightly suffered, but not so much as to irritate the XYL too much. And I heard Mr. ACZ in there. Good evening, Peter, also. So back to you, Chris. VK3AML, VK3GLC.
Have we got any other breakers before we move on? VK3AML, standing by. Nope. Anyway, yeah, interesting about DSL and ADSL. It seems that the interference that I used to experience from ADSL seems to have disappeared now that most of my neighbours are using cable and NBN. But it used to be that every time they increased the speed of from dial-up to DSL to ADSL, etc., the interference band on HF would move up in frequency, initially only affecting, 160 and part of 80 metres, then moving up to affect 40 metres and then 20, etc., etc. Now it's moved up so far that if I do experience that interference, it's usually 40 metres and above, and 160 is completely clear, paradoxically. Should be the other way around, natural noise. So we round to Peter, and I'm sorry I missed the meeting last week, but we had a bit of a crisis with Prue and recovery, and I needed to be around for that Monday night. And I have seen a bit of your camping expedition with Jim, VK3AMN, in the Mallee, which unusually was a little bit wet. And you managed to find a part of the Mallee that actually had trees you could string wires up into. A lot of the Mallee is sort of head height growth, sort of stuff. The only viable antenna you could put up would be a beverage for receiving, which only has to be at head height but very, very long in terms of wavelength. So, Peter, how have things been? VK3ACZ and group VK3AML.
And we say morning.
G'day, John.
Yeah, very fascinating. I just finished listening to those two presentations you had on YouTube.
Good evening, Gary, Dave, Graham, Chris and John there. If I'm sounding very different, no, it still is me. Unfortunately, during this week I came down with the plague. Got it from Sandra, who has just had a little cough and not much else. Unfortunately, I've been contemplating how sick you have to be to die. It's been a shocker for me, a horrible thumping headache, aching all over. I was in some respiratory distress last night. I thought about taking myself off to hospital, and I think wanting to be treated like a leper is the last thing I really wanted, so I had to be desperate. But I've been surviving on a little bit of 5-year out-of-date Valium that I found in the medicine cupboard to try and calm me down when I get these respiratory distress times. But anyway, not good fun. Now, Chris, I was going to invite you next Saturday to up to One Tree Hill, where I intend to play some the VHF UHF Field Day portable, but I suppose it's out of the question. Dave would probably know how long I'm likely to be infectious. The stuff I've read on the internet is very vague. It just says, quarantine for 7 days, but who knows what that means. But anyway, enough of the whining and the whinging. Thank you for a fascinating test transmission tonight. OFDM, I liked how the fella said that Telegraph was just the first form of internet, and yeah, I'd never thought of it that way, but obviously it is, just minus the trolls, I suppose. And W1PJE, is it PJE? Yeah, I looked up his QRZ page. There's some fascinating stuff in there. I couldn't read through it all, but I'll have a look later. Loved how he said that Dr. Phil studies the things that make you pull your hair out. Indeed. And also where he made the point where it doesn't really matter if Marconi did what he claimed to do or not. Enough other people came along with the interest and got things going. And it started to answer some of the questions I have, Chris. For example, when we were on our trip away to Little Desert National Park, I was keen on joining the Coral Coast net on 40 metres, 7093. And Eileen VK2FIVE up in Sydney is the local relay. Well, I could hear the net control in Rockhampton, but couldn't hear her at all. And of course, suddenly, sometime after sunrise, the switch got flicked, and she was coming in 20 over 9. And I couldn't figure out what that was, but I wonder if it wasn't just that the E layer starts up, or maybe it's the F1 layer suddenly appearing too. I guess we'll never know. And it's funny, I sometimes put the stomach pump on Jim about this propagation thing, and sometimes he has an explanation for me, at other times he says, you're asking questions that I don't think anybody really knows. But it's good to see that he's, Dr. Phil, that is going to all that work. And I know too that the numbers, like the solar flux numbers and the smooth sunspot number and all that, K index, A index and all that, have some sort of relation to propagation, but not always. I'm reminded that just recently Peter 3YE had that amazing QSO both ways on milliwatts with G4AKC in Blackpool, England, when the solar figures said CRAP. Funny thing, with the solar flux today up at 150 and smooth sunspot number of nearly 150, I thought the 15-metre Ansinet today would be fantastic. It wasn't. We had all sorts of problems. So, yeah, there's a depth of stuff we still don't understand. And the last real question I've got is that which radio signals, which bands leave the atmosphere and go off into space and which don't, or do they all go into space? I'd love somebody to explain that someday. But anyway, I hope you're hearing me okay with this raspy, horrible voice. It's painful being alive at the moment. VK3. Oh, and that's I should warn everybody: don't get too close to your speakers. I wouldn't want this virus to come out and grab you. Hi. VK3AML in the group. VK3ACZ.
And VK3ACZ and group VK3AML. Yeah, I'm sorry to hear about that, Pete. I would have looked forward to going up One Tree Hill. In fact, I've lined up Terry, FTJS, on the other side of the city for a test of EasyPower digital slow scan from up there, and we'll see how low we can go in power before he loses me. I suspect that from up there it'll be like putting a 1 kilowatt linear on any FM VHF that I take. The only question is, will my front end withstand all of the VHF crud that necessarily there's going to be intercepted up on that hilltop? It's an interesting one. So yeah, best of luck with getting better, and interesting that you did some HF experiments from out in the Mallee. I should imagine it will be absolutely free of man-made interference way out there, particularly those red soil tracks I saw Qam take the video of through the front window of his vehicle. I won't call it a car, it's more a Land Rover type thing, I think. Anyway, John, around to you. Nice to hear your good audio as always, John. You're obviously feeding audio into the VCO directly and tailoring the response rather than putting it through the usual preamp and limitations. VK3G to take, VK3AML and group.
Yeah, fine. 3AML, VK3EGG. Yes, that was very fascinating, those two presentations, the one about OFDM and the other one about the Ionosphere and all that. Some of that I've read before, but yes. Well, I don't think you missed much with the club meeting. I turned up there and it was all in darkness. There was no one there. So obviously they were a bit erratic in how they have their club meetings, because if it's meant to be the first Monday of the month, which it is, and I checked on their website, it didn't say anything about them not being on. So they had no meeting. So that's the truth of that one. Yes, so what else? Yes, well, I've often wondered with that thing about getting too close to your speakers. I remember I was talking about a bit of a silly thing about, imagine if TV was two-way and they had a cooking show. You'd see a million cat's paws and dog snouts and all the rest suddenly jump into the studio and eat everything before it could be shown on TV. But anyway, yes, I'll put it back to whoever it is to take it.
No worries, John. I'll hand it back to Dave, 3ECG, and I will be listening to you, Dave, but I'll be diving for the smallest room in the house, which is about 5 feet in my left direction. I better put the the microphone off while I do it, but I'll be listening to you through the speaker through the open door. VK3ECG and group VK3AML, who's diving for the small room.
Yes, VK3ECG. Yes, fine there, Chris. Well, I better keep this over just at a reasonable time limit to fit in with your... well, I was going to comment on prostates, but we won't go there. No, and I'm sorry to hear you've had the bug, Peter. As I said, I had it about 4 weeks ago now, and it wasn't particularly pleasant, but it wasn't too bad. But then I suppose I'd had the 4 vaccines and so on. So that was probably the sort of saving grace in that sort of sense. But the headache was there, and the cough and so on. And I got this email because I'd registered with the, I think it's Eastern Health for me, and so they just monitored you every single day, and you had to fill in a questionnaire online every day, which I did, and then they came back and said you might want to talk to your GP about getting some butyrcyanide, which is the that inhaled steroid that they talk about for people with persistent coughs, because I had quite a cough for a while, and then. but I actually decided I didn't want to go down that path. But anyway, obviously checking with the GP is the best thing you can do in those sort of situations and see what they come up with. But it's just not pleasant, and it just knocked me out for a good week, and then left me with a nasty cough for a couple of weeks, and so after that, although I didn't feel particularly bad, but the fatigue was what got me. I think just made me very tired, and that took 2 or 3 weeks to really get out and get free, but get free of all that sort of stuff. Yes, sorry, I turned off my sort of squelch. It's not particularly sensitive on this radio, and so I could hear everyone. So good evening to you, Gary, John, and of course Graham as well. And yes, I've not really looked at much of the EasyPal stuff. I had a problem with my PC not running the software, but it was a really very, very old PC, so one of the ones they sold off at work for sort of $100 or something. So but I recently took one of my daughter's PCs that she no longer wants, and I built that up a little bit, and so that's a little bit better. So I shall try running the software again and see if I can get a bit better luck with it. But I did like your was it yes, the Facebook video, Chris, well, it was a YouTube video, but the Facebook post around the LED display with Mario. I remember going to would have been, I don't know, Hong Kong, or actually I was in Tokyo once, and endless of these LCD displays all over the place. It's the most incredible light shows in just about every shop you can think of, and extraordinary. But I mean, it's quite obviously quite fun things, and it's a very trendy thing to do in those sort of places. What else I had down there as notes, but I'm sure you have. You are finished your ablutions and duties, and I'll put it back to you, Chris. VK3AML and the group VK3ECG.
Yeah, thanks, Dave. For those who didn't see what he's referring to in terms of display technology, anybody who has known me for any length of time will know that I've been fascinated by the history of television, particularly in the days of mechanical television, mechanical scanning. And I noticed as I was passing a tobacconist's shop at Forest Hill, of all places, they had a new display device, which I'll just show on the stream, if you care to look in on the stream. Here we go. Mechanical Television Lives, a novelty display device with a single bar of modulated multicolour LEDs rotated in a plastic enclosure. And they're sold as a holographic display. They look like a holographic display, but of course they can only scan in 2 dimensions. But this is really impressive. Inside a plastic enclosure, it looks like the image is floating on nothing. And you see this image forming. I found it absolutely mesmerising. Here we go. I'll turn down the background noise there, but you can see that it consists of about, I think, 300 LEDs in a single horizontal bar that's rotated like a fan at high speed. Each of the LEDs is modulated RGB. So it produces a circular image in full colour. There's Mario. And I was looking at this and just quite taken with it and thinking, well, John Logie Baird gets the last laugh. CRT technology is dead. Mechanical television lives. And then I went to the GOMIX site, GOMIX, and found that this is only the smallest model they make. They make them up to, I think, 1.5 metres in diameter, and they can actually synchronise fans for an entire wall to reproduce huge images. Unfortunately, because it's a persistence of vision device, frequently you get these problems with strobing between trying to video them and looking just directly at the scene, and there you see the effect of strobing with a video camera. I could only capture part of that radial image, but it was very, very impressive, the best I've seen. Gomex, perhaps I shouldn't have mentioned the company for the sake of avoiding advertising, but have a look at their site. It just goes to show that all sorts of display devices are now becoming viable with high output LEDs, particularly in the television and scanning sense, and mechanical television is right back with us. So with that, I'll hand it over to VK3DLW Graham, who was talking about the Jindalee project. Is it a long time since you're involved with Jindalee, Graham, and how much of it are you at liberty to talk about? Can they detect boats of boat people or whatever? Perhaps that's getting onto a too political an area, but just in general terms, are they looking for ships? Are they looking for aircraft? VK3DLW and the group VK3AML.
Yeah, VK3AML, VK3DLW, but well, I can answer that with a yes, but that's probably about all I should say with regard to detection capabilities. I think I shouldn't stray too far there, but no, I was involved for some years. I went back to DSTO in 1984 and was in the, what was it called, the Cybernetic Electronics Group in Electronics Research Laboratory. So they did a lot of the stuff for the original prototype, I guess you'd call it, radar at Alice Springs, JFAS, and then I went off to do other things for a while in DSTO. For my sins, I was a staff engineer for a while, and also involved in some automatic hydraulic test equipment for the F-111. But then eventually I joined the project when Telstra was allocated the contract, and I worked there for 6 years. I basically stayed on. I departed and chose to depart when Telstra decided that they didn't want to continue with the project because Frank Blunt, in his wisdom, decided that he didn't want any sort of risk like that on the books for one of the sell-offs of Telstra, the taxpayer-owned company that they then sold to taxpayers. And yeah, so I was involved for 6 years at that stage, and then I went off consulting, and yeah, then and then ended up back at Telstra again about 7 years later. You should know more, 2014. So yeah, but that was nothing to do with Jindalee. So no, it was an interesting project, and yes, as you say, it's out in the middle of the nowhere with sand until it gets flooded, and then. And it got flooded while the project was still under construction, so it made life pretty interesting at that point. And as for club meetings, John, the website you need to watch is VK3KID.org. I've been caught out the other way around once by not watching that site and found the meeting had been a week earlier. It had been up on that website for some time before the normal date, which is the first Monday, that it would actually be on the second Monday, which is the 13th. So you need to look at that site before the due date of the meeting, and it did say that it had been shifted to the 13th because of the radio camp. So it's a shame. It's not very nice to turn up to a meeting when yeah, there's nobody around. But yes, it did say on that site that it had been shifted, and that was before the normal meeting date. And yeah, well, I'll be interested to know when you are going to try Easy Pal from One Tree Hill, Chris, because yeah, I mean, it's a I should imagine you'll be able to reach me pretty easily. I mean, the Fernie Creek repeater here is like 60/9. You're 60/9 here normally, so I should imagine you could probably run a picowatt pretty well, just about, and I could catch that. And yeah, that's a fascinating LED display. It did come up on the feed about 2 or 3 minutes after you mentioned it on there. My feed's running a little bit behind. I think I accidentally paused it at one time, so that's probably part of the reason. And yeah, no, they do some interesting stuff. I mean, even 10 years ago when they did a concert of Jeff Wayne's War of the Worlds, we were treated to a holographic version of Richard Burton doing the dialogue, because yeah, he departed the planet at that stage, and of course it was his voice on that recording. So yeah, they did an extremely good job. It was live other than that, but my daughter and I enjoyed that very much. She actually found it and bought me tickets as a birthday present, I think, and we went along together. Anyhow, back to you, VK3AML, the group VK3DLW.
VK3DLW and group VK3AML, very interesting. And yes, they if they stack two of their 1.5 metre so-called video fans, the Gomix video fan, I think they call it holographic fan, but there's no 3D about it, and it's certainly not holography. It sort of has that look of holography. You can actually see an image and see past it, because the fan is rotating and you don't see much of the blades when they're rotating really fast. So it's marketed as a holographic 3D device. It's not really 3D. The surrounding scenery that you can see through the image is 3D. But you could project a picture of a person that's full size, and with two of those working together, and they can synchronize them. There is a synchronizing cable arrangement, so you can synchronize more than one of those holographic fans together and make a big image. They actually have a demonstration on site. I'll probably run a few of their advertising clips just to show the capabilities of this new technology. Totally mechanical scannings, mechanical television of the John Logie Baird type, just updated 90 years, and with, of course, LEDs being linearly modulatable, and now with very, very bright output, they've solved all of the problems of low definition and low light output that the original mechanical scanners had. So old technology that disappeared pre-war is suddenly being revived with the instrumentation, with the componentry of the present time. With the EasyPal, yeah, I thanks to VK3FTZD Tim, I've managed to get a second-hand Windows-based tablet, a 10-inch tablet, that can run EasyPal, so I take that with me, a tiny interface, which I have here somewhere. Can actually show you it, the size of two matchboxes stuck together, really. Transmit level, receive level, and that's the plug that goes into the computer, and at the other end of it, that DIN plug goes into the back of my Yaesu radio in the so-called digital input, and with EasyPal, away we go with a tablet. The only problem with that system is that the tablet's fairly dim. So to work it in sunlight, I have this dark cloth, which, like a 19th century photographer, I have to throw over my head and the tablet to see to see the pictures properly. Could be better, but all considered, it produces some pretty spectacular results. I've actually used it portable from Columbia Park at Tom VK3FTOM's field days. I've also used it on my own up near the Glen Waverley Police Academy, where halfway through the transmission, Jeff, VK3VJS, turned up and turned an interesting day into a very interesting day. So such things are possible. I've never tried it from up in the Dandenongs, and it'll be very interesting to see how far it can get. I would imagine from up there, with the 30 watts that I can run with a lithium battery, that I'll be able to get through to Ballarat or parts of Ballarat from up there. Possibilities. VK3GLC and the group VK3AML. Over to you, Gary.
Yeah, thanks, Chris. I nearly dropped the microphone. I should have rolled the chair over a bit closer to the radio, but I've got two dogs laying here. Might have to make this my last one because I think they're looking to go back up to the house to settle down for the night. I'm getting a pair of evil eyeballs looking at me, so better do that. And really haven't got anything further to add on the subject, other than the fact that in the days when we did DSL properly, all of the DSLAMs had a specific line profile for the various speed rates that you're allocated to a service, and within those particular profiles we took extreme care to notch out certain frequency bands of interest for both, of course, commercial and amateur, and of course, as the various technologies evolved, those profiles were migrated over to the new technologies, and so on and so forth. But unfortunately, in these uncertain days, with many and varied providers, and a whole lot of people that don't really know what they're doing, I'd say that's all gone out the window. I actually was going to check those just out of curiosity during this last stint back at controlling the universe, but unfortunately my access level was a bit lower than I had before I left the first time, and wasn't really able to check those out in the raw form, so I'm none the wiser. So I'm pretty certain that it's still Rafferty's rules. So and that's not going to change anytime soon, unfortunately. And I used to know someone who worked on the Jinder Lee project, chap by the name of Adrian Snell, VK5ZSN. Not sure where he fitted into the system. He certainly wasn't with I don't think he was with Telstra, unless he was on a remote contract. There was a lot of them floating around at the time. Somebody did ask me about it, but I was busy heading in other directions, so I sort of gave that one a miss. But all very exciting stuff. But all right, chaps, I'll leave you with it for tonight, and I'll wander out and into the cold and settle the canines down. Back to you, Chris, and thanks for running the session. VK3AML and the group VK3GLC.
VK3GLC and group VK3AML. Well, thank you for popping up, Gary. It's very much appreciated. And I know that parts of the sessions tonight could be a little bit on the dry side, but I just felt that it was necessary to have some mathematical explanation of the principle of orthogonality. I think I'm going to have to go back through that presentation by Jeremy Clark and listen to it a couple of times, and then look up orthogonality and OFDM and do a bit more reading on exactly how the orthogonality works out. But I gather the timing and the phasing of adjacent subcarriers allows the subcarriers' sidebands to be interleaved, thereby effectively, in terms of bandwidth, forcing a 2 metre wide device to go through a 1 metre wide opening, literally squeezing something that normally would be unsqueezable. I remember years ago on 160 metres on those very interesting crossbands that Tony used to have back, my predecessor with the 3AML call, used to have back in the 70s, was this principle that you couldn't bandwidth reduce a 3 kilohertz wide audio channel by any means without losing intelligibility. Like you could frequency halve and then double to get back the bandwidth again, but you would lose a lot through that process. Well, it seems that they've broken the rule. I mean, things like high compression audio codecs for speech have done that to some extent. It's like transmitting how can I put it, with the digital audio codecs are like transmitting the piano roll of a performance rather than the sound of the piano, if you get what I'm talking about. So, around to VK3ACZ, Peter, and I hope you're still staying alive at this stage and you haven't faded away with that COVID. It sounds like a good hot toddy and a night's sleep will be doing you a lot of good. VK3ACZ and group, looking forward to seeing you again as soon as you're better and non-infective, Peter. VK3AML.
Yeah, VK3AML and the group VK3ACZ. Well, when it feels like my head's in a vice and being crushed and pounded into oblivion, there's no one I want to give it to anybody, except Vladimir Putin, maybe. I think he deserves it, but I can't think of anybody else. But, Graham's a bit of a quiet achiever. I never cease to be amazed at what he's done with his career in the technological and electronics scheme of things. And Graham, your signal's fantastic, given that there's 2,000 feet of dirt between you and me. You're still 20 over 9. And John, yes, Graham covered why the hall was in darkness when you went there on the first Monday. We did have. It was certainly a worthwhile radio camp, despite the fact that the solar flux ducked under 100, so there was very little activity on the 12 and 10 metres. I brought squid poles and flower pots all prepared for mallee-sized trees without the possibility of getting much height, but as you saw, we didn't need to worry. Jim 3AML had his G5RV up at about 70 feet or something like that, which was pretty good, and certainly worked a fair bit of DX. But anyway, and War of the Worlds, 1977. Yes, I don't think anybody could have narrated it better than Richard Burton. That voice, those golden tonsils. And because I've lost somebody precious to me, if I hear the song Forever Autumn, I usually get very moist-eyed. It was certainly a great concept to turn the H.G. Wells story into a musical of sorts, a modern musical anyway, with people like David Essex, Julie Covington, and Justin Hayward, of course, and a cast of others, Jeff Wayne, Jeff Lynne, Jeff Wayne, one of those. Anyway, what else did I have to put in here? No, that's about it for this over. Oh, one last thing. I don't know whether you, Chris, heard from FTOM, but I got a very excited phone call from him a couple of days ago, and he said, guess what, I passed. And I thought, don't tell me he's got his standard or advanced ticket, but no, he got his driver's license. So he was very, very excited and needed to tell people. So, and I'd be very surprised if he treats it as a right rather than a serious responsibility. I don't know. I get the feeling that I don't think he'd be a hoon. Hope I'm right, but that's my impression. I expect him to be a sensible road user when he's behind the wheel at any time. Back to you, Chris. VK3AML and the group VK3ACZ.
VK3ACZ and group VK3AML. Well, I'm sure the first thing he's going to do if he gets a car is to shove a radio in it, so he may get picked up for using the microphone where he shouldn't do it. I don't know. Just on the subject of squid poles, something I haven't mentioned, I did a deal a couple of weeks ago with Warren Moulton VK3LX for a few pieces of equipment, which I showed last week. A forest phone, AWA forest phone for 160 metres, single channel thing. An ATU, and a couple of Audimax audio peak limiters, one of which is working and one's a bit iffy. But there was one other thing I got, and it's very old. It's probably about 1960 vintage, but it's a Traeger Outback portable mast. It's like a metal, well, a galvanised iron version of a squid pole. It fits into a pack that's roughly the same size, 2 metres tall, in a sort of a canvas, long, narrow canvas bag, 2 metres tall. But it extends in sections, and it'd be about 15 metres tall. It's extraordinary. So I think this is going to become part of my portable pack. That, being steel instead of being a squid pole fiberglass, has sufficient side thrust. It can probably support a small beam antenna, and that has possibilities for VHF, UHF. So going up mountains, Belgrave Heights or One Tree Hill, I may, by the time we get up there, Peter, have better equipment than I had previously. And John, yes, I heard from Peter 3ACZ before the meeting was due that the meeting had been postponed 1 week from the normal first Monday of the month because of the club camping trip to the Little Desert. So I didn't turn up. But the trouble is I was told that it was going to happen the next week and was unable to turn up because of things happening here. Hope you're still with us, John. VK3GG and group, VK3AML.
Yeah, 3AML, VK3GG. Yeah, well, I put Sherbrooke Radio Club in, and of course you get a whole page, because the trouble with these radio clubs, they keep updating websites and leaving the old one up, so you've got so many things to look at. You find after you've done all the looking up that you were looking at the one that was 10 years old the next day after things went on and all this nonsense. Why can't these radio clubs, the HRSA is just as bad, take down their old websites when they put up new ones? But anyway, yes, yes, that antenna you're talking about, I've got a military thing, all nice and army green, that's pretty much like that in a bag, and it's about 15 metres high when you set it up. Yes, Eric Burton, War of the Worlds, yes, that was a very good album. I bought that way back then, and of course I've still got it, yes, and Forever Autumn is actually a very good track there. What else was going to say? Oh yeah, they still haven't fixed RML. I'm line of sight here, and at first I thought it was a radio, so I got a Wax on and a few other radios, and it was just as bad on all of them, so I know it wasn't the radio. And then Nigel piped up and said it was just as bad at his place, so yes, I guess lightning or something hit it and blew up the amplifier or something, or whatever's happened, and it's not really working. So that's the things I have to comment on there. VK3EGG by. I hope I haven't forgotten anything this time.
No, John, it sounds like we've got the same antenna, the Traeger Adelaide antenna from about 60 years ago, the portable. Have you ever worked out what exact antenna configuration Traeger used with that thing?
No, I haven't. Originally Soap got it for me.
Oh, I see. Okay. There are a few of them around apparently, but I'm very glad to get it because it certainly has advantages over squid poles where you have any situation where you have side thrust. It can resist that quite a bit. If you tie the bottom down, it can resist side thrust a lot more than flexy, tapered fiberglass. So you could probably put an inverted L antenna with that at the far end quite viably. Yeah, okay, so it's back to VK3, which now? VK3CG, Dave, to take. We've got a big group on tonight, 1, 2, 3, 4, 5 respondents. VK3CG and the group VK3AML.
Yeah, just a quick comment. Yes, I remember I put up all my antennas as a temporary thing for HF, held up by squib poles, so they lasted for some 8 or 9 years, and then they all shattered and fell down in the wind because it was a temporary thing waiting for the building to be built. And of course now I'm not on HF because every time I want to do anything there's another gas bill or another this or another that, and I just have to postpone things, and it gets postponed and postponed and postponed and nothing happens. Anyway, take it.
Okay, over to you, Dave. VK3ECG and group VK3AML.
Yeah, VK3AML group VK3ECG. Yes, fine. Yeah, I certainly remember the War of the Worlds album, the Jeff Wayne thing, and yeah, every now and then I come across these sort of interesting historical, historical really, but they are, I suppose, recordings, and think, oh, I used to have that album or whatever it is, and I'll now download it on my sort of Apple iTunes or something like that. And I've come across a few things like that. I remember there was the Emerson, Lake and Palmer Pictures of an Exhibition, which was I think it was a live recording actually, but and again all that sort of prog rock type of interesting stuff of that sort of era, fascinating things. Yes, I've got a couple of those poles and things which for my portable setup, and they're not metal. I mean, I think they SOTA make these, or SOTA beams make these. Which company it is now? These carbon fibre ones, which are really small, incredibly light, and incredibly expensive, I might add. But of course, they're being carbon fibre, they're conductive as well. So you have to be a bit careful with them. But I've got a small fiberglass. I think it's a 6 metre pole that's quite small, and easily goes actually in the side of the backpack, and that's what I've used to put up my 20 metre inverted V dipole out on the hills, and that's been quite fun, and not too heavy to carry, and easy to either guy or which is, I think it's the one you saw, Chris, actually, when I was out at Columbia Park and so on. But it works extremely well, and it's really reasonably quite light to carry and things like that. But I think that's where I saw you using your cloth over the head easy pal technique with your sort of. I just wanted to see the flash powder go off at the side there, but as in the old photography and the plates, but certainly a useful approach. Although a bright screen would help. But there we are. Look, I'm not going to hold it very long because I've got something on tomorrow, so I'm going to try and get a bit of sleep a little bit earlier. So I might say cheerio, everyone, and get well soon, Peter. Unfortunately, you're probably in for just another week or so of a bit of fatigue and stuff, but hopefully all will come good, and you will have the voice back. I went back to, I think, my singing last week, and although I've lost the sort of top 4 or 5 notes of my register, that has slowly come back, and I'd say now my voice is probably as good as it's going to get, if I can put it that way. Anyway, I'll say cheerio, everyone, and thanks very much for the videos tonight. Chris, really very, very interesting, and whilst the maths was a little bit beyond me, I certainly understood the broad principles, and the stratosphere stuff and the propagation stuff was absolutely fascinating, and just nice to have an explanation of those charts and graphs and things that I've seen before but never really looked at with a great deal of sort of cross-referencing of the explanation of what they all showed. So it was nice to have someone go through and explain exactly what they were. I found that very, very useful indeed. Thanks very much. 17 to everyone, and listen around hopefully next weekend. All the best. VK3 ECG. Clear off back to you, Chris. Cheerio, everyone.
Yeah, I might say morning too.
Okay, all the best, John. All the best, Dave. And Dave, next week's session will be on partly on the restoration, digital restoration of audio off very early discs. I probably will use just trying to think of his name, Henry VIII Dances, recorded in 1916 by Edward German. Edward German conducting the orchestra with his own compositions as an example to iron out the frequency response variations due to a horn and a diaphragm and the air cavities and the stylus armature that drives the diaphragm, and how all that can be flattened out using a waterfall display as the analysing device for the frequency response variations, and then parametric and graphic equalizers digitally applied to bring the stuff back to sounding somewhat like a modern recording. Can be done. I don't know why more people don't do it. Perhaps just that people that collect early recordings aren't so technical. But anyway, that'll be next week. And if Jeremy Clark VE3PKC is listening, you've reminded me, Jeremy, how mathematically based a lot of the modern means of communications are becoming, particularly with the association with computers for decoding, so that I have to go back to books of differential calculus and Fourier analysis that I would have read last at Swinburne Tech 50 years ago, brush up on that, because I got out of electrical engineering and went across to become initially a radio presenter and then later researching in the film industry. So it was more journalistic than anything the way I went. So I left the maths behind, and it's 5 decades and I really need to brush it up. But I will watch Jeremy Clark's presentation a couple more times just to assimilate orthogonality and the various other principles that he described in his talk on OFDM. So thank you to VE3PKC for expanding our consciousness in that direction, and likewise Phil, thank you both for the permission to run those videos. I'm very glad I was able to get them, and they just by chance, one being 1 hour and the other one being 30 minutes, fit into our 90-minute slot beautifully. So with that, Gary 3GLC has signed off. It looks like you're tying the ribbons, Peter 3ACZ, if you're still there, VK3AML.
Yeah, VK3AML and the group VK3ACZ, and yes, I'll make this my last as well. Really starting to wear out. John mentioned that RML's been off the air for a fair while. I'm kind of surprised. I think it's ARV's repeater, isn't it? Since it gets so much use, I thought it would be a priority to work on. I remember REC was off the air for a long time, but I think the quarantining and curfews and all the rest, 5K limits and all that was part of the problem there. And thanks for the best wishes from you, Dave. My Sandra had the 4 jabs, and perhaps that's why she's just got a minor cough and no other real symptoms at all, and I'm so glad she has. I turned up for my 4th only to be told that I wasn't eligible because of my age, so I wasted an hour sitting around for that. But by the same token, Chris, I've been contemplating what on earth did I go through the routine of getting all the jabs, although, yeah, maybe it wouldn't be so bad. Can't think of much else. Gary's gone. Dave, Graham, and you, Chris, thanks for another informative and thoroughly fascinating test transmission. Already looking forward to next week. Whatever it is, I know it'll be good. And until then, have a great week. VK3AML, 7-3 everybody, VK3ACZ.
Yeah, thanks, Peter. Just a final call. Does anybody else want to call in before we close permanently? VK3AML just standing by.
VK3VJS.
Ah, Jeff, g'day. How are you? VK3VJS will be finishing us off by the sound of it. VK3AML.
Yeah, okay. Just climbed into the virtuous bed.
Very virtuous there, Chris. Very chaste as well. I watched most of it. That first session was a little bit over my head, but I found the second one very interesting, etc. And I've been listening to a lot of the comments. So thank you again. And as I said on the note, I had Anthony here earlier on, and of course he had a bit of time to kill. So I fed him, watered him, and kicked him out. I don't know where he went, but I've got a fair guess. So that's all okay, Chris. Anyway, thank you again, and good evening to everyone listening. Good morning to everyone listening. I really enjoyed it, Chris. So keep up the good work, and hope Prue is well. Oh, okay, I've seen Dave ASE's YouTube. He's now laird of the manor up there, 60 acres. And it looks like he's got a couple of outhouses, then outstations, they're not toilets, and a couple of cars I see there. And it looks as if the people just left the property, walked off it. There seems to be a hell of a lot of stuff around in the container and other places, so that's very interesting. Anyway, all the best, Chris, and thanks again. VK3AML, VK3VJS.
Yeah, no worries, Jeff. It'll be very interesting to see if Dave 3ASE has sufficient interest to follow through on that suggestion that he might get a shortwave broadcasting license. And he was talking about getting one somewhere in the 2.3 megahertz region. And these days, from what I've heard, shortwave broadcasting licenses for those bands considered to be non-international are relatively inexpensive to access, and it would be very interesting to see what he does with the whole idea. He certainly has the equipment, the technical expertise, and the enthusiasm to follow that through if he so desires. But I suspect that he'll be setting himself up at the new premises for some time before that would be a priority. Okay, final call. Anybody else for a final comment before we close? VK3 Alpha Mike Lima.
Yeah, just to wish Peter a speedy recovery. VK3DLW.
No worries, Graham. I'm sure he's got that. I'll stand by.
Yeah, thanks, Graham. Cheers, everybody.
All the best, Peter. Next time we hear you, probably your voice will be an octave higher. Oh, dear. Okay. Well, with thanks again to Jeremy Clark VE3PKC of Toronto for his talk on OFDM, which really will send me back to my technical school maths books and quite a bit of reading on OFDM on internet. And to Phil Erickson, to both of you, thank you for being so gracious as to allow me to run this on our Saturday night sessions. We're always appreciative of material that's mind expanding, and certainly Jeremy's paper particularly was at the edge of my understanding, sometimes with the maths slightly stepping over that. I will have to see about redressing that situation with some suitable reading. So this is VK3AML now closing on 147.475. Good night all. Thank you all for being on. Thank you to the people on the stream. Robert Varner, KC2TEL from New Jersey, has been listening in on the stream. And Pirate, whoever he might be. Clint Jeffrey, VK3CJS, I think. Or is it CSJ? I think it's CSJ. Harbs Electronics Lab VK2XYP in Sydney has been looking in, so I think we had a peak viewership of about 22. We're down to 11 now. So to the 11 that are on the stream, and to those who will be watching this on replay, all the best to you. Next week we'll be up on 9:30 p.m. Melbourne time, 11:30 a.m. UTC, for another 2.5 or perhaps 3 hour session of the VK3AML regular Saturday night live streaming. So good night to you all. VK3AML now clear.
Good night, and thanks again, Chris.
Cheers, Jeff.
Yep, thanks, Chris. 73s.
All the best, Graham. Okay. And I'll just fade that down, and thank you particularly to the people on the stream. The graciousness of Jeremy Clark and Dr. Phil Erickson in Massachusetts and Toronto. What an extraordinary world it is that we're living in, where we can combine ham radio with a video component and produce a viable result that has potential for learning as well as communication. Very happy to be a part of all of this. VK3 Alpha Mike Lima, now wishing you all a very good night, and hoping to catch you next week for a bit on audio restoration and the usage of waterfall displays to analyse audio and thereby correct it. No longer do we have to correct the frequency response of material by ear. We can actually measure with a waterfall display where the resonances, dips and limitations of audio are. So to all of you, a very good night, and thank you for being there. I sincerely appreciate all of the participation.